Welcome to APEC Open Mic. It's March 30th, and I'm your moderator, Tim Ventura. I want to give a giant thank you to everybody who's joining us on today's call, along with everybody who's watching us on YouTube. So as a reminder, today's session is for open discussion and ad hoc presentations. We don't schedule those in advance, but we do have a couple of attendees who have reached out and asked to present. John Brandenburg, I believe, has two different things he wants to discuss, and then Jim Decker sent one over as well. So we want to try and get those in, and we also want lots of open discussion, which is really what this session is all about. So I'm excited to get started with all of this, but I do want to start you out with a couple of quick reminders. You can view conference replays, details, and speaker info on our website at altpropulsion.com. The open mic sessions go up typically about a day or so after we record these. Those are on the Alt Propulsion YouTube channel. So if you haven't subscribed to that, please subscribe to that now. And that way you can view everything that's going up. I try and put timestamps in as much as possible. That way we can kind of go through and see, where various people are discussing and presenting things. So again, altpropulsion.com and our YouTube channel, which you can link to from the website. So during the ad hoc presentations, please try and save questions for after the presenter finishes, if possible. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can also type questions into chat, and we will try and get them. A lot of times the chat fills up with discussion, so it's hard to pull questions out of that. So the absolute best way, again, is Option Y on Mac or Alt Y on Windows to raise your hand. We're not going to be firm on hand raising during open mic unless things get chaotic. So I want to try and encourage you to jump in when it feels appropriate, right? With appropriate comments and questions and things like that. And let's try and keep things focused on the core topics of the alt propulsion community, as well as, when people are doing presentations, keeping it focused kind of on what they're presenting as well. So I think that is everything for now. Again, welcome everybody. Just as kind of a side thought, happy Easter weekend to everybody. My 80-year-old mother informed me that this is Easter weekend. And so our attendance may be a little bit lighter than usual, and that is totally cool. That's one of the reasons that we record these. So I am going to unspotlight myself, and I'm going to allow folks to unmute themselves. Should we, I guess this would be up to you guys. Should we just jump right into presentations, or do you want to do like little 10 or 15 minute kind of overviews for the first hour or so?
Overview would be nice.
Does anybody have any breaking news to share with us?
I have
good lab updates
and again,
on my
everybody is currently muted, but you can unmute yourselves. Let me see. We have Phil, who's having camera issues. Norm Breeze is here. We've got actually about 35 people. Pretty busy today.
As for myself, I just wanted to show something.
I'll tell you what, since it's quiet, why don't I do this? I'll just jump right into Mr. Brandenburg. John, why don't I spotlight you for the audience? And let me ask you to unmute.
Okay. I think I have some stuff that'll be very interesting to everybody. I made some progress on the gem theory. Quite remarkable, what I believe is kind of a mathematical breakthrough, mostly of academic interest, but it has to do with the quantization of gravity fields. And then I also have another short piece on some preliminary results from a model I am developing of high temperature superconductivity, something of great interest technologically. But let me first make the presentation on this, what looks like a mathematical breakthrough to me in quantum gravity, a coherent kind of overall theory addressing the great issues of quantum gravity. Most people who are aware of the state of quantum gravity theory know that it's catastrophically unstable the way they have tried to do it. Immediately you end up with a bunch of unstable waves of gravity, gravity quanta going unstable and bifurcating basically into shorter and shorter wavelengths in kind of a turbulent cascade like you see in hydrodynamics, which they can now show in simulations. And so this turbulent cascade to shorter and shorter wavelengths leads ultimately to a whole bunch of black holes forming, and the whole universe disappears into an array of black holes. Something we don't want to happen. So, you'll pardon me, I'm a little bit under the weather. I just moved up to Oregon, and it is a lot colder and wetter here in Oregon than it is in Texas. And so I'm adjusting to the climate. But anyway, Tim, do you have the presentation?
I do. And so, John, if you want, if you want to put those up, this is Zoom, so you can share your screen and share those.
Oh,
directly.
I can share screen. Okay.
Yeah.
Let me.
And you know what? I owe everybody an apology too. I may have goofed up here at the beginning. So when I was asking for people to speak up, my AirPods were not connected.
Oh dear. Oh dear. So if you want, we can go back to and
well, you know,
let the
I think
conversation be open. But I was hoping people would be popping popcorn by now and getting ready for this.
Yeah, let's push
dazzling
forward.
Dazzling piece of math that I have discovered.
Let's push forward with yours. Leonardo, let me see. Let's stop your screen sharing. Okay.
Okay. Let's see. Okay, share screen.
Yeah.
And then I can let me okay, it's a I guess okay, it says whiteboard or what does it say?
So share, so you click that green square. Do you have, and then it'll bring up a list of files. Do you have your files open? Do you have your presentation?
No, but I can open them very quickly.
Yeah,
I have them
open them up.
Very much handy for this. And okay, I have 2 PowerPoints, which are, I think, are the best things to use in this forum. Let's see. Okay, let me open one. In fact, I'll open the other one also, just so that we can go without any delay.
Yeah. And let me apologize to everybody for the chaos today in general, but hey, you know, it's a holiday.
Never apologize for chaos, Tim. Chaos is part of life.
That's right. That's our community. We are chaos. So
we are chaos. And that's why we are feared in certain quarters. We are feared. Let's see.
This is why I don't believe in conspiracies. The government doesn't have to do it. We do it to ourselves. No conspiracy required. So
okay, can people see the title page?
Okay. No, so you have it open. So click the green screen share button down at the bottom.
Okay, pardon me here. Let me okay, I open, and then the green screen. Okay, here we go. Back to Zoom. Okay, it says okay, it says, whoops, excuse me.
There we go.
Okay.
There we go. You're getting there.
Oh, we got it?
Something is sharing. Okay, it says you've started screen sharing. There we go. So it looks like you're sharing your entire screen. So if you want to maximize that slideshow, that'll work.
Well, yeah, right now. Besides, I may.
There we go.
Betray distracting. I may betray distracting.
I see famous scientists. I see
or things. But anyway, semi-classical approach to quantum gravity through the gem theory. And so people can see that?
Yeah.
Okay. And there's, of course, Stephen Hawking, and of course, Big Al, Einstein, and somebody whom a lot of people haven't heard a lot about, a very important figure in physics around the same time as Einstein. Einstein, she was sort of a protege of Einstein. And named Lise Meitner, and she actually discovered nuclear power. She discovered that by splitting, that they were splitting uranium atoms, and that they were releasing more neutrons that could create other splittings of atoms, and that was releasing energy when it did so. So she was the actual discoverer in her theoretical analysis of nuclear power, but she never got the Nobel Prize for it because she was Jewish, and she was the Swedes. Nobel Prize has always been very political, and she had taken shelter from the Holocaust in Sweden, and the Swedes thought at the time the Germans were going to win the war. And so they didn't want to offend the Germans by making this Jewish woman a Nobel Prize winner. So they just basically ignored her and gave the Nobel Prize for discovering fission to Otto Hahn, who was her collaborator. So it all got straightened out after the war. She had the last laugh, but there she is, as you can see, quite an impressive looking personality and absolutely brilliant. And so she discovered nuclear power, but she also was the muse to discover something else, which I'll be discussing today. So anyway, without further ado or introduction, okay, the agenda for today I'm going to discuss, and I'll move through this fairly quickly, and I've left out a lot of mathematical steps, which normally I like to belabor, just to cut to the chase. But anyway, we'll talk the basic theory of quantum gravity through the gem theory. The gem theory, of course, unifies gravity and electromagnetism, at least in a working model, similar to Hal-Puthoff's. But the interesting thing about the gem theory is, since it uses the quantum E&M as a basis, that can carry that quantum character into the gravity theory. Now, I'll discuss the two problems with quantum gravity in its present state, what's called the catastrophe and the abyss. And I'll explain what those mean in a minute. And anyway, so we talk about the solution to the catastrophe, and we also talk about crossing the abyss, the two great barriers to quantum gravity in the present community. The gravity, and then I'll discuss, I'll show in, after omitting a lot of mathematical details, I'll show the quantum gravity, the gravity correction to the mass energy for an isolated electron. Very important calculation. And then I will summarize. So, basic concepts of quantum gravity from GEM. E&M theory can be quantized. We all know that because of Dick Feynman, QED. And key to that is the Poynting field. The Poynting field is what carries momentum and energy in the electromagnetic field, and that's the thing that gets quantized in photons with spin one bosons. So the GEM theory uses the Poynting vector to make gravity. That's the interesting thing about the GEM theory. The Poynting theory is also the center, not only of quantum electrodynamics, but it's the center of the GEM theory. Therefore, models of gravity fields can be quantized through the Poynting vector quantization that already has been worked out by Dick Feynman and others. Now, so we say, oh, well, since you can quantize, you can unify gravity in NM, and you can quantize E&M theory, that means you can just carry this quantization through the back door into gravity theory and have a quantum gravity theory. No, it sounds very straightforward, but it is not. There are tremendous barriers that are recognized by the community to having a quantum, physical quantum gravity theory. First problem is that the quantum gravity quanta have mass. Photons in electromagnetism don't have charge, so they don't serve as source terms. But in quantum gravity, the quanta actually have mass, so they also serve as source terms for further gravitons, meaning you can get a feeding frenzy. And what this leads to is in simulations they've done of gravity, a bunch of gravity waves running around in the universe, is they're subject to turbulent cascade, to micro and forming of an array of micro black holes, which causes the entire universe to collapse. This is a good term for this is the catastrophe. So we naturally don't want the universe to disappear into a cloud of black holes. Now, gravity, so that, but anyway, that seems to be an people have tried and tried to get around this problem and they can't. Fact is, gravity quanta have mass. So you can have a turbulent, you have a cascade to shorter wavelengths like quantum, like hydrodynamic turbulence, and only the turbulence then generates negative mass or positive mass, and anyway, it goes unstable. So gravity originates at much longer wavelengths than most E&M. So there's this tremendous gap. We apply E&M at a bunch of wavelengths characteristic of subatomic particles, size of subatomic particles, classical, Compton radius of the electron, or classical radius of the electron, etc. Those are the kind of scales of wavelengths of photons. And but gravity, by definition, must originate at much longer wavelengths. So there's this tremendous abyss, this tremendous bottomless gap, apparently, between gravity theory as we know it exists in the universe, which would have to exist at long wavelengths, and the much shorter wavelengths that E&M theory operates at as a practical matter. So that's the abyss. How to couple something at very long wavelengths, gravity, to something at much shorter wavelengths, E&M theory of subatomic particles. So these problems must be solved before quantum gem gravity can work. So there are two very powerful barriers to a quantum field theory, even if you have the gem theory. Now, here is quantum gravity needs to solve the catastrophe. The catastrophe is very easily represented, by the way, with transition of laminar fluid flow to turbulent flow. As here, this is in infrared or an infrared shadowgraph of a column of hot air rising from a Bunsen burner, and at some point it goes from being laminar to developing long wavelength, a little crooked part of the thing from turbulence, to suddenly going into what's called a turbulent cascade, where it suddenly develops turbulence at much shorter wavelengths than the original length scales of, and this is determined by, of course, the Reynolds number. So this is a transition between, you can see that turbulent transition. Now, when they do simulations of gravity theory, they get the same turbulent cascade, what's called a turbulent cascade, meaning energy starts out in long wavelength modes and ends up very quickly coupling to a whole avalanche of short wavelength modes of shorter and shorter wavelengths that, of course, then at shorter and shorter wavelengths, the gravitons weigh more and more. So the whole thing becomes a negative energy catastrophe. So the gravity waves break up into a turbulent cascade like turbulent fluids. They've seen this in simulations. And gravity waves turn into then an ensemble of black holes. So that's the catastrophe. And of course, we've detected gravity waves. They're very long wavelength, put out by stars and colliding black holes and things. And so obviously they propagated across the universe without going unstable into And we don't pick up a lot of high frequency gravity waves with these gravity wave detectors we have now. So anyway, just to show you a picture of, here's an energy injection at long wavelengths to make a bunch of vortices and fuel fluid. The vortices split into smaller vortices, and they split and split and split till finally they get so small that they're basically the size of molecules, and the molecular collisions turn them into heat. Now that's what happens in an ordinary fluid in the lab, but in quantum gravity, there's no friction to get rid of the small black holes. That just keeps cascading down forever. So now, as it turns out, there's a solution to this, and it's actually in the literature. This solution to this was invented by Stephen Hawking. It's Hawking evaporation. Short wavelength gravity waves turn into black holes, which have a turbulent cascade. So this turns into micro black holes, which are destroyed by Hawking evaporation. The smaller the black hole, the faster it decays into E and M gamma rays. So you actually have gravity field disturbances that actually turn into pure E and M gamma rays. So the turbulent gravity waves, if they do a turbulent cascade, turns into a cloud of E and M photons. It doesn't turn into a bunch of black holes that then destroy the universe. So the catastrophe, once you realize that gravity is an aspect of electromagnetism, the catastrophe is short-circuited by the details of E and M at short wavelengths. The short wavelength limit is where E and M couples directly to gravity in terms of these black holes. So that problem, the problem of catastrophe, can be kind of mathematically solved. Now, the abyss, how do long wavelength gravity E and M fields turn into quantum gravity fields, which must, so you end up with short wavelength quantum E and M fields, and you'd think they'd kind of resonate with short wavelength gravity fields, but that's not what happens. The gravity fields, photons have much, much longer wavelength than anything that transitions in subatomic particle interactions. So the answer is, how do long wavelength short wavelength quantum E and M fields turn into long wavelength gravity fields crossing the abyss? Well, the answer is very slowly. Gravity is much weaker than E and M at subatomic scales. Even though gravity must arise from these tiny masses, it doesn't, its coupling is very slow and very weak because it's weak. So work with the simplest particle. Let's work with one isolated electron, which in quantum mechanics is considered a point particle. But if it was a point particle, just in classical electrodynamics, sitting in a vacuum, it would have infinite mass. And of course it doesn't. So what happens is you have vacuum polarization, or the quantum reaction of the vacuum to the point charge electron. And if you come up with just a simple, so you can write the E and M field as not just E squared, but it's E times D, the electric field times the displacement field, familiar from conventional quantum. We're trying to do a semi-classical approach, a classical kind of E and M expression. So you have an electric field, and we assume the electric field saturates at a certain radius around the point charge due to quantum vacuum polarization. And I'll be discussing that in a little bit more detail. But the displacement field knows it's still a point charge, so it has a singularity in it, whereas the singularity disappears from the electric field. Now, when you do this mathematical model, which interestingly enough, by the way, is this is the Schwarzschild solution to the gravity field equations for a metric, only this one has a plus sign instead of a negative sign. So no black hole forms. Instead, you get E field saturation around the point charge. So if you look at this integral of E dot D, you get this integral, and that can be integrated. I mean, this is just a simple semi-classical model. It's an approximation. And what happens is you end up with your standard E squared over R naught, which becomes the classical electron radius. You can imagine the electron can be modeled as just a shell of infinitesimally thin shell of charge. But then there's a correction term due to the quantum fields, and that correction term goes away as you go more and more towards a point charge approximation. So for R prime, less than R naught, but also of the same kind of order of magnitude, at least approximately, we have this expression, and this expression is due to what's called Delbrook scattering, and it means in a quantum viewpoint, photons around imagine a point charge being surrounded by a cloud of photons coming kind of in and out. They're kind of all just hovering around this point charge, and they start running into each other, and that creates the vacuum polarization effects. And what comes out is this very interesting vortex pattern of the photons approach each other, split into electron-positron pairs that then annihilate. So the photons actually kind of run into each other and then bounce off each other with two different photons. So you have two photons come in from different directions, and then they kind of run into each other, and they bounce off each other just like two billiard balls. But they fly off in different directions with different energies. And so the thing that can describe this in quantum electrodynamics is what was first discovered by Delbrook, a guy who he was a brilliant scientist, and he worked, interestingly enough, for this woman. She was his mentor and his thesis advisor. And she was also the discoverer of nuclear fission, the fact that you could split uranium atoms and it would release more neutrons and also release energy when it did this. So you could have a chain reaction producing energy, more and more energy. And but Delbrook had a very interesting history. He became a biologist. He wasn't a physics guy. He just needed a doctoral thesis, so he got a doctoral thesis in physics, but then he went off and did biophysics, biology. So the real inspiration, apparently, for his work was Meitner, who was everybody knew was just a brilliant person, and so this bit of unifying E&M and gravity, which, as it turns out, what this leads to, was actually the inspiration inspired by Meitner. Now, you can imagine, since it's a point charge, that you finally end up with Delbrook scattering at the Planck scale, which is where quantum black holes appear and disappear. And now, because you end up doing long wavelength averaging, the expressions for Delbrook scattering change, and it becomes effectively kind of a nonlinear interaction. It looks like a classical nonlinear interaction, but actually it's mediated by quantum fields, and it's kind of the saturation field strength around a point charge due to vacuum polarization. The fact you put this negative charge in the vacuum and positive charges virtual positive charges appear to kind of partially screen it. So the electric field basically saturates, leading to a finite mass. It's neutralizing charge. It affects its observed mass, its effective mass. But down here on the bottom of this, this term is E1, and that is the part due to the singularity, the electric fields due to the singularity near the point charge that haven't saturated, or at least before the quantum thing can neutralize them, they are not saturated. And because of the long wavelength averaging, that's what shows up in this calculation. And what it is Planck length. The charges of all the particles become h bar c, e squared. Instead of e squared, it's h bar c, which has the same units as e squared. So it's an effective charge increases by about 137, and now this vortex pattern radiates a graviton every time it occurs. So when the two photons run into each other and do this elaborate interchange of electrons and they both split into electrons and positrons and do this vortex, that serves as a source for a gravity wave. And if you look at the quantum angular momentum for photons, a pair of photons basically unite or interact, and what comes out the other side is a graviton, and gravitons have two h bar as their angular momentum. Instead of being they're still bosons, but instead of having just a single unit of spin, they have a double unit of spin. So the interactions down at the very, very intense E fields and vacuum polarization near the Planck length form gravitons, and that's where the gravitons occur. The gravitons occur because in the cloud of charge, a cloud of photons, virtual photons popping in and out of existence because of quantum uncertainty in the vacuum that helps neutralize the charge around a point charge. Some of those photons run into each other and they make spin 2 gravitons when that happens. And so we can get an expression for if we have an electron sitting in space and we're trying to do all the quantum corrections to its mass. Its first is a kind of just what is its standard mass term, let's using the classical electron radius. But then there's this correction term that goes away as we go to smaller and smaller wavelengths. But this one doesn't go completely away because it stops at the Planck length. You can't go any deeper than that. Lengths are no longer physical at that length, at that scale. It's no longer, space-time is a foam. You can't get any closer to the point charge than a Planck length. So this is a cutoff. So that's where the gravitons are generated by photon scattering generates gravitons rather than just other photons. So, and this is the mathematical expression, and you notice there's a negative sign. If you put a charge particle out there and it acquires a certain effective mass due to its charges, and then it's the vacuum polarization partially neutralizing the charges, so you end up with E squared over R naught, which is a classical electron radius. But as it turns out, there is a correction because all masses have a slight negative mass contribution due to the fact of gravity. The Earth, if you broke the Earth up into a whole bunch of little pieces, and this is in Meissner, Thorne, and Wheeler, if you broke up the Earth, God forbid, into a bunch of space dust and scattered it all over the solar system, it would weigh more, slightly more than when you assemble the Earth into its present form. And the reason is that when you assemble the masses together, that creates energy, and to compensate for that energy, you have to have a negative mass term due to gravity energy. So the gravity self-interaction is negative. And so it's a correction term to the electron mass. Now, let's look at this in more detail. Well, if you do all of the numbers, according to Delbrook scattering down at the Planck scale, and making sure that you use the long wavelength averaging, this is what you get. You get the mass of the electron, mass energy of the electron, and then an energy term that is minus, and it's big G times the mass of the electron squared over R0, its classical electron radius. So quantum E&M leads to quantum gravity through Delbrook scattering, which was the muse of that, the midwife of that discovery was Lise Meitner. So mass correction to electron mass from gravity arises Delbrook scattering at Planck scale. So the math works. It gives big G times mass squared over 0 over the effective radius of the electron if it was just a shell of charge. So, in summary, gravity can be quantized semi-classically through gem theory, apparently. Hawking evaporation eliminates the catastrophic cascade to micro black holes. Suddenly, gravity waves can, of course, have a turbulent cascade, but that doesn't lead to a catastrophe. The catastrophe becomes a bunch of virtual E&M photons. It turns into thermal photons, basically. So then the Delbrook scattering at the quantum scale, which is where the original gravitons come from, produces gravitons from pairs of scattering E&M photons. Gravity mass source is E&M fields. The gem theory basically pretends that there's only two forces, all it concentrates on just the long-range forces of nature. There are only two force fields. There's gravity fields and E&M fields, and the gravity fields have mass, and that serves as the source term for gravity. So gravity mass, the cascade of gravity turbulence turns into E&M photons, and the gravity mass source is E&M photons caused by photon-photon scattering. So the gravitons arise from quantum E&M Delbrook scattering and are stabilized by Hawking decay into E&M photons. So it starts with E&M, becomes gravity, and then decays back into E&M. There. That is my summary, and I've got this up on ResearchGate under this title. So I was quite excited.
Okay, so John,
make this mathematical discovery. Yes.
You have one more for us too, right?
Yes, I do. I have
okay,
a brief,
do you
a brief one. Do you want me to just launch into that?
Yeah, just launch into that one, and then we'll
just launch into it. All right.
This is Casual Saturday.
Okay,
so
here's a simple theory of high temperature superconductivity. As you know, there's quite a bit of excitement.
Oh, and John, can you maximize that? Sorry, my friend.
Oh, I'm sorry. Terribly sorry. Okay. I have been talking for many months now with Michael Perrone and his group. We were all excited, of course, about the initial reports of a room temperature superconductor. Then everybody said, oh, no, we can't reproduce that. Oops, pardon me. It's supposed to do a full thing. Here, hold on. Okay, there. Is that, everybody see that?
Yep. It's
Hello?
perfect. It's perfect.
Oh, okay. Very good. Very good. This one is much simpler and much shorter. Uh, I'm developing the mathematical models, but those are sort of a work in progress. So I decided, well, especially because I was going to concentrate on the gravity thing, I'll basically present the conceptual roadmap for this simple theory of high temperature superconductivity. Now, we were all excited about the reports of room temperature superconductor, and I do believe we will find that substance. It's possible. We have now found it. They have new results showing a complete levitation of the objects, what's called the Meissner effect, and flux pinning. This at this point looks like the real deal. And I told Mike, I said, Mike, we have a real opportunity here, Michael, because the rest of the community has already dismissed this. Meaning, if you realize they've actually found something, and I have a theory we can put together to show you how to improve it, then we can surge way out ahead of these people before they finally get over their pathological skepticism and wake up to the fact that a breakthrough has actually been made. So anyway, Michael, if you're listening, the field is wide open. But here's the simple theory. Most people are not aware that even though they have a very well worked out theory for very low temperature superconductors, things like lead or niobium titanium, linoleum, tin, that work at liquid helium temperatures, like 4 degrees Kelvin. Okay, they've worked that theory out well, and those are very simple substances. They're just basically you can just take plain lead. It'll turn into a nice cheap superconductor. Or you can take niobium, pure niobium, or mix it with some tin or titanium to enhance it a little bit. But these are very simple kinds of substances. Then what was completely unexpected was some people mixed together copper with yttrium and barium, two rather alkali metals, and oxygen, and you wouldn't think that would do anything except be something you could make coffee mugs out of. But instead, at liquid nitrogen temperatures, roughly 30 times higher temperatures than the low temperature superconductor. And let me tell you, liquid nitrogen is as cheap as milk. It's just very readily available. And if you can run stuff on liquid nitrogen temperatures rather than liquid helium, which is expensive, helium is rare, and getting things down to 4 degrees K is very expensive. So if you can run things on liquid nitrogen, that's much, much better. Now, we have a good theory that says low temperature superconductor niobium. Just take pure niobium. Conduction band electrons, and niobium conducts electricity. It's just not very well. It's a pretty punk conductor. But if you chill it down to liquid helium, it becomes a superconductor. And the mechanism is that conduction band electrons form Cooper pairs. The pairs of electrons get together and they actually dig a potential hole in the lattice potential, electromagnetic potential, electrostatic potential. And so they form pairs there, and those become bosons, which means you can get a Bose-Einstein condensate, and you get the Meissner effect and all the things we associate with superconductivity. So now, most people are not aware that even though we have a good theory for low temperature superconductors, we don't have any theory at all after gosh, almost 40 years of high temperature superconductivity. This stuff is, for one thing, it's complicated. It's a complicated chemical, typically, and we don't know why it goes. How can you form Cooper pairs in this mess of chemistry? The only really fascinating thing to me is it's at its heart is copper. So it's like improved copper. We've taken copper from nature and improved on it. And copper, by the way, is a really punk superconductor. You got to get really low temperature before it becomes a superconductor. The best superconductors, by the way, at low temperatures are actually poorer conductors at room temperature than like copper and silver. And you can mix silver, by the way, with the high temperature superconductivity, and it seems to work just fine. Silver and copper are chemically very similar. So we have no theory for high temperature superconductivity that anyone believes. People have some, back of the envelope ideas, but none of them have caught on, and none of them have. Nobody's gotten a Nobel Prize for this stuff. They got a prize for discovering it, but that was in the lab. No one has explained it. So now let's make the assumption that Cooper pair electron populations do form in YCBO, which is just your standard high temperature superconductor. Yttrium, copper, barium, oxygen. So I have come up with a model. I'm not going to show you the mathematics today. For one thing, it's still a work in progress, but I call it the electron GT, give and take model of Cooper pair formation in YCBO. So what we're trying to do is explain how do you get superconductivity in a complicated chemical like YCBO at a much higher temperature than for like niobium or lead or something like that. If we have a theory for high temperature superconductivity that works, then it's just a matter of figuring out how to raise that temperature by making the right choices and some educated guesses using this new model I'm developing. And we can get the room temperature, or in fact, we can explain and help improve the high temperature superconductor, the room temperature superconductor they've just now invented, which apparently does work after all. So the electron GT theory, and then I'm going to summarize. Okay, but I'm going to go through this quickly now, since I was going to try and put some math models in here, but I just thought, oh my God, they're not well developed enough to present. So niobium is ordinary superconductor, and anyway, it has a transition at 9.25 degrees K, T sub C. However, and it becomes a superconductor. It's a punk conductor at room temperature, but it's superconducting. But at 9 degrees Kelvin, it becomes a superconductor. And the electrons deform the lattice electron clouds. You have a bunch of electrons that are disattached from the lattice, and they're floating along kind of above it in a higher energy state, slightly higher. And then you've got a bunch of gaps, holes. You've got electrons, and then you've got a bunch of holes in the lattice, which are positive, and they attract the well depth. So anyway, if you can get that lattice to quiet down, then you can actually get electrons getting together and forming, deforming the local lattice, forming Cooper pairs that cling together, and they form then bosons, producing the Meissner effect. So here's niobium conductivity. Conduction band electrons and lattice potential is bumpy. So they have a bumpy ride. So there's a lot of resistance. Now, when you have niobium superconductivity, you have Cooper pairs forming in these much shallower lattice potentials. And so if you can raise the temperature, or as long as the temperature doesn't get too high, so the lattice starts vibrating a lot and destroy these potential wells, you can have superconductivity. Okay, that's niobium, pure niobium. Okay, now we get to real world. YCBO, why can't anything be simple? It's improved copper. Improved copper. The copper atoms float in a sea of electrons from donor atoms. I think I spelled donor wrong, pardon me. Well, I tried to I actually, the spell correctors gave Donner, like Donner Pass. I thought we don't want to go there. So Donner, Donner atoms, alkalis. Okay. So it's a combination of copper, which is, a fairly non-reactive metal, but it's mixed with two very powerful alkalis, yttrium and barium. These are electron rejectors. They want to get rid of their electrons, so they have complete electron shells. And then the receiver is oxygen. They form ionic bonds, where the electrons go and fill up the last oxygen shell on the oxygen. So everybody's happy with full electron shells. And what they're doing is you're sharing these electrons, and above this is floating these copper atoms. So assume the sea of electrons being passed between alkali and acid elements fill up the positive scattering wells. Imagine that they fill up all the wells in the copper cavity, allowing freer movement of copper conduction electrons. So the holes in the copper lattice potential disappear. They're basically filled up by this passage of this trade in electrons between the acid oxygen and the alkaline yttrium and barium. So they're passing electrons back and forth, and in the process, it fills up all these holes in the copper lattice. Okay, so that's the give and the take. So imagine then that the sea of electrons also makes formation, that it becomes this group of electrons, this electron sea of the acid and alkaline elements formed by them exchanging electrons. This sea of electrons interpenetrating the copper clouds of electrons makes formation of positive wells. The electron potential, the potential electrons of the copper sea are far more malleable, and they have a deeper trapping energy. So they can form copper pairs that survive even at 75K, almost 10 times higher temperature than the liquid nitrogen temperature as opposed to liquid helium temperature. So the Meissner effect, they've even gotten it even higher than that. So now they're claiming, of course, at 273K, which is room temperature. So we have then YCBO superconductivity is a bunch of Cooper pairs forming in the copper conduction band plus the C electrons, the electrons that are being exchanged. It's like the copper is stuck down in a valley, and the two very powerful electron givers and electron takers, the oxygen and the alkaline, the acid and the alkaline, are flipping back electrons between them, and those combine with the electrons of the copper to make a much easier system to form Cooper pairs. So, summary. The GT give and take model of high temperature superconductivity can explain the gross behavior of high temperature and low temperature superconductors. Like I said, I wanted to present at least an equation or two from this, but I'll have to do that at a later date. Basically, the acid alkaline atoms contribute a sea of extra electrons to both conducting electrons and lattice charge density, allowing Cooper pairs to form at higher temperatures. It's the presence of the acid and the alkaline, the tension between those, that actually kind of straightens out all the bumps that the electrons from the copper see in trying to form superconducting Cooper pairs. So the GT model can be refined to explain how room temperature superconductors can be achieved. I do believe that, and I'll be presenting on that at a later date in more detail as the math, the problems that start developing in the math model, I can solve them. I know I can solve it. But anyway, so the GT model can explain high temperature superconductivity as due to this acid alkaline component mixed with the copper that improves the copper. How about that? So you got improved copper. So anyway, guys, that's it. And that I think this model can lead to explaining the high temperature, the room temperature superconductors, and showing how to make them very robust so that they hover right over the way above the magnets rather than just in a very thin elevation. So anyway, very good.
Awesome.
That's all I have to say. My heart is empty, as the Native Americans used to say after giving a speech. My heart is empty.
In a good way, John. So let me do this. I'm going to remove spotlight and let me stop you sharing. Hold on.
Oh, okay. Here. Okay. Yeah. Let me.
There we go. Stop sharing.
Okay. Oops. Stop sharing. Okay. Stop sharing.
There we go. Okay. Yeah. And everybody, let's put our hands together for Dr. John Brandenburg. Thank you.
Hey, thanks a lot. You know, what is the sound of one hand clapping? That's swish, 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 swish.
Swish, swish.
But I don't hear that. I hear two hands clapping.
Well, you would never hear one hand clapping. That's the whole idea behind one hand clapping. So
I can disprove that. You just let your fingers loose.
Let me go to Rick. Rick has his hand up. Rick, go for it, sir.
Okay, John, can I talk about your Mars theory that it was nuked?
Yeah, sure. You want to do that? Let's talk about it.
I was talking to Bing today. I was researching Mars and possible nuclear explosions. And
right.
Bing searches the whole internet, and he said that it's possible that in the crust of Mars, there's natural fission reactors.
Like
uranium.
Thank you, Rick, for bringing that up.
He said that because Mars lacks plate tectonics and the water doesn't go underground much, that there was no moderator, and it could lead to an explosion 25 times larger than the SAR bomb from Russia. And I was thinking of your theory because I saw you present on this twice. And the Bings showed me some areas on Mars that actually might be areas that had the explosions. And it said over the billion years or so, the dust storms covered it up. And with the radar that they used, they could actually pick it up if they look for it. That was Bing's idea. So I thought I'd just share it with you.
You're talking about Bing as if it's a person. That's an AI.
I know. I have a lot of conversations with AI.
Talk about non-human intelligence. I mean,
that's really actually quite brilliant.
You seem to think that it was an alien, somebody nuked it, but I was thinking more of a natural explosion.
Oh no, Rick, your point is very valid. And in fact, that was my original theory.
Okay.
Was that it was a natural nuke because we had those on Earth, and I presented it at the Lunar and Planetary Science, and people liked the idea. They said, well, if it happened on Earth, it could happen on Mars, and there is groundwater on Mars, which it turns out, though, you need, in order to make that work, you have to have moderation on the neutrons, simply because the uranium will not fission with fast neutrons.
Okay.
So it's an important physics thing. You have to have slow neutrons to get this to work. And what happens when they found this in Africa, the water would get into the uranium deposits, very rich uranium deposits. And this is a billion years ago. So all of the uranium was actually enriched reactor grade in those days, because the uranium-235 decays over time. So a billion years ago was all 3% U-235. So just bear with me. So yes, my initial theory was this was natural. But what happened is they said, people came up to me and said to me, That's fine, John, but that doesn't make a lot of xenon 129. It doesn't. Those are slow neutrons. To
How
make
about,
xenon
how
1,
about, how about thorium?
oh, well, thorium will not even fission
Okay.
unless it's a fast neutron.
Well,
Okay.
hold on. What if I
No,
mean,
no. So the way a thorium reactor works is you actually have to start it with uranium, irradiate a bunch of thorium to make uranium-233, which then can fission with low temperature neutrons. And once again, you have to have to get a thorium reactor, you have to have moderation.
well, so there's quartz, like the oxygen in the quartz would be a moderator, right? I mean, the hydrogen. Is
No,
better.
well, the best moderator is hydrogen.
Hmm.
I
What
would
So that's
think,
why the uranium deposits down in Africa, they discovered, water vapor. Oh, you'll love this, you guys. The water vapor invaded these uranium deposits, got these natural nuclear reactors running, and then it got hot. So the hot temperatures drove out the water, so it shut down. So it went in cycles.
John, I thought water moderated so it slowed down the reaction. On Mars, there wouldn't.
No,
be
it
would
slows down.
explode.
No, Rick, it slows down the neutrons,
The
which
water,
actually
yes.
enhances the reaction. You can't have the enhanced reaction in order to have something that runs on pure uranium, you have to have it very compact, like in a bomb. You have to have weapons grade uranium in a very compact
But
thing.
nobody really knows what's under the surface on Mars because nobody's ever seen it. So how would we know?
Well, I mean, we know what happened on Earth, and
Well, Mars is
if that, here's the other thing, Rick. I looked at this. I tried to actually get it published in a journal. You know what they said? They said if it blew up, if natural nuclear reactors blew up on Mars, it would make big craters, right?
Yes, but over the billions of years, the dust storms covered it up.
Well, so that sounds like a conspiracy theory to me that there's a cover up on Mars.
No, nobody just.
I'm just kidding. No,
nobody found it yet because nobody looked for it with the radar.
Well, look, the signs are the hot spots of radioactivity are at two basic sites, and they're full of thorium, which is a component in nuclear weapons to enhance their neutron output. By the way, remember the Amchatka test of the nuclear warhead up in Alaska? That was full of thorium.
Okay.
So then you've got potassium, which gets irradiated by neutrons, and it stays radioactive for billions of years. It's got a very long memory. So we find two hotspots on Mars, but there's no craters. There's nothing.
Hey,
it's
John,
just flat as a piece of paper. It's the old ocean bottom, in fact. So then here's the other thing. The xenon spectrum from a nuclear reactor, operating nuclear reactor with moderation, which is the only way you can get one to work in nature. You can't get a weapons grade nuclear reactor working. You have to have water to moderate it, and that produces a lot of xenon 132. It doesn't produce any xenon 129 to speak of. The only thing that produces xenon 129 is a hydrogen bomb or a supernova, where you've got fast neutrons.
Hey, John, did you read that they just used the radar to find at the equator that there was a lot of water frozen under the ground?
Like, oh, yeah, it didn't surprise me at all. By the way, I'm the guy who discovered the Mars ocean. Look it up on Wikipedia. I'm reference number 1, but they never give me credit. The rascals.
That's the ultimate compliment, John.
It is the ultimate. I am he whose name must not be mentioned on Mars.
I get a lot of ultimate compliments too, so.
Oh yeah, it is. And no, Rick, your question is very good. I considered that carefully, and it just did not match the data I had.
Okay.
The thing is, it doesn't produce, the natural nuclear reactors don't produce xenon-129 in any quantity to speak of. And if they blew up, which they would have had to release this much energy, they would have created big craters. And some of the craters on Mars have been around since the very beginning of Mars. They're still there.
Hey, John, I sent the conversation from Bing to your LinkedIn page. I sent you a message with it. If you want to look.
I don't want to argue with any damn robot.
Okay. All right.
Okay, here's the thing. Here's the thing, Rick. Recently, in fact, I asked anybody. Elon Musk apparently was being interviewed about Mars recently. This was just reported to me the other day, and he started going off on xenon-129 and nuclear holocaust on Mars. Is anyone aware of an interview like that?
No.
I'm trying to find it.
Like, I never saw it. But thank you very much, John. You helped me a lot.
Anyway, Rick, your question is very good. It's a rather technical question, as it turns out. It's a physics question, and I hope I have tried to I have answered it.
Yes, you have. Thank you.
You could still be right. You could still be right.
Nobody really knows until we put boots on the ground.
Well, yeah, nobody knows, do they?
That's what Elon's
got boots on the ground.
That's what Elon's working on.
That's right. That's right. He is. And somebody reported to me that he was in an interview talking about this whole issue, which amazed me. I thought, why doesn't he call me or send me a check?
Thank you, John.
Anyway, thank you very much, Rick, for your question.
Awesome. Rick, thank you. Let me see. We got hands up. Let me go to Mr. Norman Breeze next. Norman, go for it, sir.
Thank you. Yeah, I really appreciate the information that you put out there. Superconducting. It's always been very interesting to me to watch that from the inception that I've seen it from. The concern that I have, I've been working with magnetic field for about 8 years. I need every possible situation that I could come up with, unfortunately, OCD with it. I found out from my own experience that the magnetic field disappears at 1985 Fahrenheit. I was trying to put my stuff together, welding it. I hit it with a torch and it was gone, just like that.
Oh yeah, there's what's called the Curie point. It wasn't discovered by Madame Curie. It was discovered by her husband. That if you heat magnets above a certain temperature, they just lose all their magnetization. They get all scrambled in there.
Yeah. The magnetic field is not like that. And the second part there is with what I do, I work with copper. It is a wonderful. Well, I was going to say it's a wonderful neighbor to magnetic field, but the truth is that copper and magnetic field, they are worst enemies. The magnetic field does not like copper, and there's a law there with that. The copper will defend itself on magnetic field, but with the copper,
especially if the magnetic field is changing rapidly, it doesn't like it.
Yes, and with what I do, it changes at a real high rate. And so also the thing that I was wondering about with the high temperature superconducting is, that the copper will liquefy above 2000 degrees. And so I don't know what your superconducting temperature would be at for the high temperature, but I thought, I just want to be careful with that.
Well, I will be. In fact, I'm going to stand far back in the lab when Michael does his
you put on welding equipment,
cooks up
all right?
this stuff, just in case.
You dress up in welding equipment. Do me a favor, dress up in welding equipment from head to toe when you do that for your own safety. I've been through too much of this. I've exploded too many magnets in my life.
Oh, absolutely. They love to explode. It's like you're telling the copper the high rate of change magnetic field.
Yes.
Won't you two get along and cooperate? And no, they won't.
So what I have found out is
a lot of coils exploded in a lot of early experiments, by the way.
Yeah, and so what I have discovered with what I do, I don't use superconducting at all, and I don't use maglev technology at all. But what I do is I found out that the magnets, yeah, they will levitate, and the temperature that I have noticed on a difference in temperature is only 1 degree Fahrenheit. Just one,
Interesting.
just one.
Well, if you spin the magnets, you can get them to levitate now. That was when I was a kid, they told me that was impossible.
Well, I sent that experiment to NASA, and then they did their experiment with it to prove what I was saying, and then they never sent the experiment back. I had to research it.
No, of course not.
And they said,
Norman, this is concerned. When you start doing stuff like this, there are people within the government start getting very nervous.
Okay, well, let me tell you what happened with me. Some of the people here are familiar with my little TikTok page that I have, and I have put a lot of information out there with it. And my daughter was going to do it professionally, and then I thought, I'm just going to put raw information out there. I did that, and within a week of me doing that, I've got 5 emails from the Department of Defense. And I got an
congratulations.
Yeah, I got an invitation from I got an invitation. I'm in Utah. Got an invitation from Hill Air Force Base here to go up in 2 weeks to present what I do to them. And so I just
so you're gonna go up and talk to them.
So wait, are you saying that copper is superconducting at 1900 Fahrenheit?
What I'm saying is that at 2000 degrees copper melts, and so then at 1983 it doesn't matter what you have next to the magnetic field, it's gone.
Well, what do you mean it's gone? Like, is it superconducting or?
Well, okay, let's put it this way: that the organization that you have with the magnetic field, it's gone. That organization, the electrical charge of it, it's gone. I know that when I put the temperature to the magnetic field, and then put ferrous or anything else next to it, it was just a piece of metal. It was gone. There was no reaction to it at all.
Norman, speaking of organizations, I just don't want to distract, but I'll just tell you, when you go up to Hill Air Force Base and show them what you have found, don't be surprised if you get a bunch of very tight-lipped characters watching it. They'll ask a few interesting questions, and then they'll say, "Thank you, Mr. Breeze. Don't let the door hit you on the way out of the building."
Well, actually,
we'll get back to you, and they never do.
Okay,
they actually gave me a contract from DARPA.
Yeah.
To study the gem theory for 2 years, and I had to smooth out a bunch of math problems with it stuff, and I did. And they told me when they gave me the money, they said it was $200,000, by the way, and they told me I was working for a company at the time, and the company was very happy with me. So so they tell me, we're giving you this money to do this experiment, to do this theoretical study over the next 2 years. And then they said, do not do any experiments.
Do not do any experiments?
Do not do any experiments. And then they said, and so then I did the work and did the theory. We'd done experiments earlier. We knew that it was there, that the effect was there. But anyway, I gave them a big report at the end of 2 years, and their reaction was, "Thank you, Dr. Brandenburg. Don't let the door hit you on the way out of the building." They wanted to know what I knew.
Yes,
And
yes,
they're going to want to find out what you know.
yes.
And you know, because there's a big,
The
I'm sorry,
problem
there's a
is,
classified program on this, and they view you as kind of like a poacher.
yes, yes, I have been watching them. Well, I got an offer from Germany and Russia 2 years ago.
Oh, and the Russians probably want you to come visit too.
Yes, yes, I got an offer from each one of them for 20 million at the time, and I turned them down.
Congratulations. You know what happened to Podletnikov, who started seeing these anti-gravity effects? He was working in Finland. The KGB basically just showed up, said, you're a Russian citizen. You're going to come back to Moscow to continue your research. And they took everything in his lab. And people have heard from him again. I mean, he's still alive, obviously, but you don't hear any new results from him.
Well, the one beautiful thing for me at this point, my dad keeps on saying to me, "Be careful, they'll steal it from you." And I told him, I said, it'll be hard for them to steal it from me because I haven't written the book yet.
Well, I said the same thing about my discovery of the Mars Ocean, and they, they just say, "Oh yeah, the Mars Ocean," and then you ask them, "Who invented the Mars Ocean?" And they just look at you blankly.
Yeah,
so it's okay. But anyway, Norman, congratulations on your work, and congratulations, your work is being recognized by the military-industrial complex. Yes.
Yeah.
See, I don't have that, but I am, this is a little known fact. I am the inventor of pizza flavored ice cream. And people have tried to steal that. The challenge is
the sound of two hands clapping.
Yay.
It was
the deaf people.
It was the 90s. It was the 90s.
But if you put that ice cream on a pizza disc and it starts to levitate, you will get a call from some of the same buddies, same friends of Norman here. They'll want you to come and bring one of these pizzas to us for us. And
can I give you a warning out here to everybody that's listening?
Yes.
I'll tell you what happened with me 3 years ago. 3 years ago, I was bored and I put not what my technology, the details of it, but what it was about on LinkedIn. The next morning, NASA had linked to me, and they have watched me ever since. And they listened to me because the stuff that I talk about to people on the phone, I find that stuff online within 6 months.
Yeah. Congratulations.
We're being listened to. So this is kind of where it's at. Is the Department of Commerce told me you can work with the Department of Defense and the public both at the same time. So I've done my homework. I'm going to say, you guys want to know what's going on. Well, guess what? You guys.
Well, when you fly over in your flying saucer for them, please wave at me in Jacksonville, Oregon.
So my whole goal is to get the oil industry off of our backs next year, and to make sure you don't have to worry about how good your tires are.
Well, guys, if it's okay, let me go to Michael. Michael is patiently had his hand up too.
I'm sorry.
Thank you,
that's
Norman.
cool. We're again.
Thank you for your report.
This is super casual Saturday, guys. So
that's great. You're doing great, Tim. This is a great meeting.
There's John wearing his hoodie and his hat. John, I have your hat. I just bought your hat. I have one of yours. I'll have to go find it.
My brother gave me this hat this afternoon. He said, if you wear a red hat around here, everybody thinks you're a MAGA Republican. And I said, well, during election year, that's probably not a good thing to do around here.
Just wear a white hat and give up.
Yeah. Well, hey, Michael, what do you got, sir?
So,
yes,
Tim, does that pizza flavored ice cream come with anchovy?
I was originally I was thinking try this, Tim. Originally, I was thinking. I don't know how that would change it. Actually, if you were really going to pull it off, you'd probably want Hawaiian pineapple. That's closer to your dessert spectrum, anyway.
It had to be in Asia
with little pieces of ham.
Yeah. So
You better come close to Hong Kong when you sell that. Sorry.
All right.
So John, my question was about the nukes on Mars, I call it.
The nukes on
Um,
Mars, yes.
So, and the possibility that it's a natural occurring thing.
Yes, it could
And
be.
so,
It could be. You know, people ask me
well,
what actually
could
happened
it
on Mars,
be?
and I'd say I don't know really.
So Mars is not doesn't have plate tectonics. It's like
It's got it. It looks like it's got a frustrated plate tectonics. On Earth, we have what's called the Great Rift Valley in Africa,
uh,
and it's this long kind of groove in Africa's deep valley with a bunch of lakes in it. And what it's part of Africa trying to separate and go out into the Indian Ocean. And on Mars, apparently the Valles Marineris, this is my interpretation, apparently the Valles Marineris represents an attempt to separate off part of the big continental plate and form a different continent that basically failed. It kind of ran out of gas. I mean, if you look at the Valles Marineris, it starts as this Greek trench, and then it stops and becomes a spiderwork of fissures. And then there's three volcanoes, and then one giant volcano. It's like all the geothermal energy that was trying to make this split finally just erupted to the surface and formed the Olympus Mons and the other volcanoes.
Supposedly, Earth was what there was a proto-planet phase of Earth, and that
yes,
got hit, and probably we got hit by a Mars-sized object.
That's correct. That's the theory.
So, but
most of the continental
the
rock
thing
ended
is,
up forming the moon.
On Earth, we know that there's uranium, for example.
Yep.
We know, so these radioisotopes, these metals that are heavier than iron. And as you probably know, in the life cycle of a star, when the fusion reaction gets to iron, that's when it blows up, when it hits iron.
Well, so, it manages to sputter along up above that. It's only to take a finally it starts making uranium and thorium, and that's about when it blows up. Those last when it gets to lead, it basically starts, the star goes unstable in the core because it can't, it's literally the end of the line, and then it blows up, and during that explosion the thorium and uranium get formed. Apparently, I
thought it was I thought they discounted all that, and they said it's a neutron star blast that generates anything.
That's the latest, iron. Right? You got to understand, science is like Hollywood. It's the latest bright. This year it's the Barbie movie.
So the question then is, what evidence do we have for naturally occurring radioisotopes on Mars?
Oh, there's the uranium. The Martian surface is constantly being bombarded with cosmic rays. It doesn't have a strong magnetic field like the Earth, so there's a certain amount of there's an elevated level of radioactivity in the rocks on Mars due to there's more cosmic rays on Mars that reach the surface. And it's also got a thin atmosphere, stuff that would break up in the Earth's atmosphere because it's dense and because of the magnetosphere. Doesn't happen on Mars, so you get more. Everything on the top couple feet of Mars is slightly radioactive, and the settlers on Mars will have to take into account of that.
Well, they don't have.
They'll probably wear lead boots. So. They'll have lead liners in their boots, when they walk around on the surface. But they'll basically live kind of underground in kind of big shopping malls with only turrets, kind of where you can go up and look at the sky, and that's what I think.
The last thing I just did a comment on the first presentation you did. I've been working on this paper for IEEE Sensor Journal on quantum gravity, and
Sure.
just yesterday I got my final preprint accepted. So
Oh,
issued.
okay. So you're publishing something?
Well, it's a preprint right now.
Yeah.
Hopefully they're gonna give me approval.
Oh no. Well,
But the fact that they gave me a preprint is a good sign. Okay, so what I'm doing
that is a good sign. Yes.
So I just put in the comment a link to that preprint, and that's all.
Oh, okay. Thank you. Well, I
Okay.
mean, no,
So
that's
yeah,
it.
you can download, if you can follow the link, you can download the article, and it's called Resolving Extra Dimensions for Gravity.
Oh, sure.
Okay, thank you.
Okay. Thank you, Michael, for your comments. They were very interesting.
Okay.
Well,
so who
like
wants
for
to
me
go?
to
I had a question
time
for
to
John.
Tim, it's time for you to get out the hook and hook me off the stage and let somebody else
Okay,
yak.
well, John,
So
thank you,
we'll have-
man. Thank you for coming today. So
Before you
let
go,
me-
John, I had a quick question, if that's
Oh,
okay.
quick question.
Oh,
All right,
okay.
Curtis.
I hope it's
I
quick.
also have a quick
Mike,
question. I need to figure out how to raise my hand here. Let's see.
in your first talk, you used in your calculations the Schwarzschild solution, at least the first
Or
part of it.
it's funny. It's also a solution to the same equations that give the Schwarzschild solution. The way they verify the Schwarzschild solution is gravity potential is, when they go to the weak field limit, it gives the right expression, which has a negative sign on it. But if you can actually put, believe it or not, a positive sign in there, and then you get this a very interesting model for just like a point charge with finite mass. It's the electric field saturates around, so it's a very physical looking solution. I'm trying to figure out, why is it in general relativity at all? Why should general relativity allow a solution like that and yet not exploit it? So I think it does exploit it, actually.
That's a good question. So what I was going to ask you about is why you picked that solution, and did you consider other solutions? Like, there is an interior solution to the Schwarzschild interior Schwarzschild solution to that Schwarzschild metric. So basically, you take a mass, and
Yes,
Schwarzschild solution is meant for
that's on
outside.
that's on the basically the outside, and then of course
Yeah,
there's the
and
inside. Yeah,
there's a
I
solution
wanted
for the
to
interior portion as well.
I I basically was concentrating on using it as an electrostatic, as just a model, interesting mathematical model for a point charge of a, like an electron in quantum. The quantum theory of the electron is that it's a point charge, but it's surrounded by a cloud of electrons and positrons that slightly neutralize its charge effectively. And yeah, it's they call it renormalization, and they said, through the miracle of renormalization, the electron doesn't have an infinite mass crushing the universe. So thank God for renormalization. Then you ask them, what does it mean? What does renormalization actually mean? And they'll walk away.
Yeah, well, on
it's
that,
just a mathematical trick they do.
Yeah, I think you could look at renormalization as a way of removing self-energies.
That's what it is. The vacuum itself in quantum mechanics has almost infinite energy. Unless you put in the Planck scale physics, it's got infinite energy. And then even then, 1 cubic centimeter of vacuum actually outweighs the visible universe. So there's a lot of stuff in quantum field theory they don't like to talk about. Yeah, it's like a haunted house. Well, nobody goes to the third floor.
G-2.
What's that?
G-2. That's the
E
latest,
minus,
right? With
what's
D
that?
minus 2, the problem with the muon calculation.
Oh, yeah, yeah.
So the reason I asked about the metric and these
Yes.
other metrics is I know that there are like several models out there for the electron. You know, there's some models that treat it like something that's moving. And so, you know, there are metrics that you could look at, like the Kerr metric, which is a rotating metric.
The spinning, yes, the spinning.
Yeah,
one.
so there are metrics that you can kind of use, and there's interior solutions to some of these. So, you know,
Yes,
it'd be
there are.
kind
I've always wanted to look more carefully at the Kerr metric, but the Schwarzschild metric kind of gives me whatever math I need right now, and so I'm just stuck with it. And you know, it gives me black holes, and then it gives me you know, this very interesting point charge, finite mass point charge solution, which I thought, why should there be kind of this electrostatic looking thing as a second solution of the Einstein equations? It's I published this, by the way, in 1992, and no one else has ever picked up on it, that this solution exists. It's interesting, but it's
Okay.
a convenient, it's a
Thank you
convenient.
for answering, John.
What's that?
Thank you for answering.
Oh, okay. I'm sorry, Curtis, if I talk too much.
No. I just want.
I love talking about this
Michael has
stuff.
his hand up.
So if I can
Michael.
jump in, yeah, hi. So if I can jump in real quick. So
Sure. I
So
was
what
very
we-
impressed by your email, by the way, showing the pictures of the stuff hovering over the magnet.
Well, oh yeah. I mean, that's not our lab's work. That's South Korea. They kept with it apparently, and now they have some positive results.
It's definitely hovering.
Yeah, that's pretty difficult to refute at this point.
I know it is.
Yeah.
But we can take advantage of the fact that everybody says, "Oh, that's a crazy result. We don't believe anything the South Koreans do at this point."
Yeah, well, I mean,
Michael, that's a golden opportunity.
yeah.
golden
So
opportunity for you.
what's the hypothesis you were posing earlier and then? So like adding rare what's it
Well, if you have ordinary copper, of course, it's a good conductor.
sure.
And then you add the acid, you add the alkaline metal. You know, copper has a, you know, tendency, it likes to bond with oxygen, but not very strongly, you know. And it's not an inert metal, but you know, it's near gold, which is kind of inert. And so copper is there, and it doesn't form really strong bonds with other things. But then you've mixed it with two very alkaline metals. Yttrium and barium are very powerful alkalins. So they want to give up electrons. They don't want these electrons because they want to have complete shells, and this outer electron is just a nuisance. In fact, it's a pair of outer electrons in the case of barium and yttrium. They want to get rid of them. So they send those outer electrons packing, and they go and attach themselves to oxygen, which is ionic, that needs two electrons. So you have something that likes to give up two electrons, eagerly gives it up, and you've got something that very eagerly grabs them. So then just imagine you've got the copper sitting in between, and it's surrounded with this cloud of electrons being kind of given and taken back between the acid and alkaline. And for some reason, adding those electrons smooths out the potential that the copper conduction band electrons see, so they can suddenly form Cooper pairs and get superconductivity. So, you know, other people say, oh no, and here's the thing, there is no viable theory for high temperature superconductors.
Well, I mean, there's a few interesting ideas like bipolar ionic conductivity and
sure, there's a few interesting ideas, but I've never heard anyone nobody's gotten a Nobel Prize for it, you know. It's been around for 40 years almost.
So I mean, in the lead copper oxypyromorphite phase with sulfur, apparently, what what alkali metal would you add to that? Because like any alkali metal you would add would potentially destabilize this. Like it would reduce the amount of sulfur that you could get in there.
I know it's I'll have more to tell you, and I'd rather talk to you about that offline at this
All right.
point. Simply because you know, I have a theory that I think explains YCBO, but what, you know, there are a bunch of other mixtures that do things like this, and
And
the model seems to work for some of those, but not for others. Like adding sulfur, I don't know. You know, that's not what I expected. You would add. The model I have right now would not say that sulfur is something you should get anywhere near these things. But you know, obviously it seems to work. So this makes me think, well, I've got to I've got to change my model and make it more flexible. And I haven't been able to do that yet.
Got you. Well, I mean, I've pulled out everything on the periodic table that readily forms oxidation state of +2.
Yes.
And I paired up everything that has similar size ratios to the lead and the copper. And there's like 5 different combinations that might do it. But then the question with many of those combinations is, like, maybe you need the transition metal, maybe you need the affinity for the sulfur to get the effect, and some of these don't have that. So the sulfur
obviously, you have a basic effect, and then you have an ability to fine tune it. There's some kind of knob that we haven't found, we haven't identified yet, and that knob is there. I am trying to find it, Michael.
Yeah.
And we'll talk offline when I do find it. I think that explains. Right now,
one practical thing that would be very helpful. Do you know anyone who makes small, like alumina crucibles? Like if you could get 100 very small alumina crucibles, you could do tests with that.
Make those
yeah, I don't.
Actually, maybe other people here would know too.
Yeah, unfortunately I don't know. I'm a plasma physicist. To me, you heat everything till the chemistry goes away and then the fun begins. But no, but I'm very into chemical physics too. You know.
So Norman sounded like he might know.
Aluminum has a very low melting temperature.
Aluminum oxide.
I'm sorry. I thought you were saying
alumina. Yeah, that's sapphire. Okay, that has a very high.
Okay, yes, and sapphire. I don't even. I'm like a break.
Yeah, a long day.
It's been a long wait.
Yeah.
Yes, it has been.
Well, John, we'll talk about it. We'll see.
Okay, Michael, we'll be talking further about this, and yeah, I'm trying to figure out. Funny, I just bought a new DVD player, and I'm trying to figure out how to get it to work because the old one was really simple, but didn't survive the move. So now I'm trying to figure out what are all these extra knobs for? What are they? You know,
all in a day's work. Well,
yes,
anyway,
okay, Michael, keep up the good work, and if I see anybody who has you know, alumina crucibles for sale.
Actually, you could just.
And by the way,
make them. You can actually make alumina crucibles.
There's a Cotronics cement.
Yeah, Cotronics. They're
yeah. So I tried that.
760 is 4,000 degrees.
Except I tried that, and they're sintered. Those ceramics are sintered together with silica nanoparticles, and then
oh my God,
the silica nanoparticles dissolve into the superconductor, and they turn it green, and it doesn't work anymore.
And then just what that's, by the way, in my field of plasma physics, they call that an unanticipated synergism. Usually that means the experiment was a failure. That was a polite way of saying the experiment was crashed and burned. We had unexpected synergism.
But yeah, Drew, you're gonna say something else there?
No, I've been using a lot of the Cotronics products,
Yeah,
some high
Cotronics is great.
temperature- Yeah, some high temperature TPS for where I work, and it's you'd be amazed at some of the stuff you can put together with basic ingredients.
Yeah, the problem with cooking up new ceramics is that when you have a porous container, like that's good for metals and stuff maybe, but then if you try to use that like cemented container to hold some other ceramic, then the ceramic will wick into it.
So you got
Especially lead-based ceramics. Lead-based ceramics love to wick into silicon nanoparticles.
amazing. So you got basically alumina put together with quartz. You got sapphire particles clung together with quartz, and that's too reactive for you.
Well, I
Actually,
think that
zirconia.
Well, they have zirconia, they have alumina, they have quartz.
Okay, sorry. I'm kind of curious about this. Does the silica does it have a similar temperature as okay, it's silica. Isn't that what or similar to the glass blowing? Or am I just way off? Is it similar to
No,
that? What they did?
blown glass is typically soda lime glass or something that melts at a much lower temperature. Pure quartz nanoparticles will melt around 1400 Celsius. But then with the other ceramics, the hope is that they will diffuse into the other stuff and mix with it and form a nice barrier. But like that's just the hope. It's if you're trying to like make ceramics in those containers, it's very difficult.
Make a lightsaber?
I'm wondering
By the way, I just before anybody departs, having one set of eyes is good, but having a bunch of set of eyes, if you guys could all look and see if you can find a thing by Elon Musk talking about Mars where he mentions the Xenon 129.
I get
recently.
email from him all the time.
Yeah, so
I guess I can email him back and ask.
Oh, also, Brendan McNamara, I just wanted to call you out. Were you the guy at Livermore, Brendan McNamara?
No, although it's very common since I'm on academia.org. I get all sorts of pings of asking me if I'm the Brendan McNamara that wrote this or that amazing thing. So no, but I get that a lot.
Are you the guy who kept us in Vietnam 5 years too long, much longer?
No, that's Robert.
That's
Robert's
terrible.
An asshole.
That's terrible.
No relation.
Don't do
no
that.
relation.
That's terrible.
Anyway,
maybe the McNamara of McNamara's band.
I got a question for you guys. For all you intelligent ears, I got a question for you. We know basically what magnets will do and won't do with the superconducting and with the maglev and so on. Has anybody tried to work with something similar to superconducting where they weren't relying on the pinning? In other words, a specific space that it was being pinned to with the superconducting.
There's type 1 superconductors, but I think all of the high temperature ones are type 2 that do flux pinning.
Okay,
that's my impression. I haven't researched that deeply, but
has anybody here tried to move mass more than the pinning with any type of magnetic field response? I know that they use ionic propulsion for the satellites, but they have to propel them off the space station. Has anybody been able to do that? From Earth?
I'm sure you could do that even without superconductors. You could make kind of a version of a maglev track,
okay,
or railgun sort of thing to shoot stuff off of the space station.
They use springs.
But if you were to remove the track,
use physical springs, guys. They don't use maglevs on the space station.
Yes,
what do they use?
Yeah,
they use little springs.
Springs.
Well, they can't handle the atmosphere to take. Has anybody done this without a track?
Done what?
Any type of maglev, any type of levitation, any type of
Oh,
propulsion
yeah.
without a track.
I've done a lot of things with high temperature superconductors where I got the magnet to hover over there, and then you bring another magnet near it, or you poke
I
it with
mean,
a
I mean,
toothpick,
what,
and you can see it tremble.
yeah,
It's as if it's in a resistive
yes, but with the
medium,
superconducting,
that won't.
it relies on a track. Have you been able to remove the track and get that?
I just used isolated pieces of superconductor, so
Yeah.
it was fun, but um, I actually built a 60 hertz thing that floated in an aluminum pan about 3 inches, 3 or 4
Yeah.
inches off the coils
Mm-hmm.
when I was in college as a science
Good.
project, and that worked great. So it can be done, and it was done stably. It was a flying saucer, basically.
So yeah, I'm just kind of I keep on checking everywhere I can find. Is anybody in the same little niche that I am where they're doing this and they aren't relying on the correlation of a track?
So where's the magnet underneath the superconductor? Is it painted on the
V-gate
tabletop or
system.
something?
Oh, I love that. Well, I don't use myself. I don't do the superconducting. Mine is on completely different concept of technology. But I was just, you guys are really smart and you have a lot of experience. And so I was just wondering, with all the experience that you have had, have you been able to work with magnetic field with solid magnets or making any type of magnetic field where
V-gate system.
you're able to get it to levitate, you're able to get it to move, have power to move away from the
V-gate
earth
system will
without a
move.
track?
Oh.
Well,
V-gate-
I spun one of those magnets, and I had it nice, so it float, and then I actually had a floating moon globe.
Yeah, they
ever
have
seen a-
toys
Norman,
like
you ever
that in
seen a
Asia
V-gate
all over the
system?
place now.
Oh,
They
I
sell
know. That's so fascinating that it's become the first place. By the way, the first place you see anything like that is in Earth versus the Flying Saucers.
Huh.
Check out the movie Earth versus the
Okay.
Flying Saucers, and they
I'll
actually
check it out.
levitate a iron sphere.
Well, and that's what I'm after, because my theory is 8 years ago I learned I could get a magnet to levitate. I sent that information to NASA. They said, okay, yeah, great, we proved that he could levitate. And they had a very much smaller one, and they put it in a vacuum. And I said, I didn't use a vacuum. Well, you guys are cheating. and so then I said to them, and I was very sarcastic with my little response. I said, great, you have a wonderful grade school science project. Now, what are you going to do with it? I asked them, I said,
and
how
they
are you going to make it work for you? You're levitating it, but can it
Norman.
work for you?
Guys, you're all barking up the wrong tree if you're asking NASA to look at something for
You hear
you
me?
to figure it out or
Norman,
give you ideas. I'm telling you, that
I've
is
been
not the
sarcastic.
organization.
You ever seen the
that
V-gate
solves
system?
these problems.
What's
Not
that?
anymore, at least.
You hear me?
I would say, Norman, you're not just barking up a wrong tree, you're barking at the moon. They are
Yeah.
Sorry,
completely.
Mike is trying to say something. Mike,
Go ahead.
did you have? Sorry,
Hey,
Mike,
Norman,
did you have?
Yeah.
how you doing?
Yes.
How about your
No.
question about moving stuff with magnets? The V-gate system specifically does that. It's a rail system, though.
It's still
It's in a
relying.
V. It's in a V, and then you have a bar magnet north and south, and it pulls.
Oh, yeah. Okay. Yeah, I'm familiar with that concept. I'm referring to being able to have the propulsion system be independent of anything like that.
The V-gate system is aligned in a V with magnets north and south, and then you have a bar magnet, and it will pull in that direction.
So
Huh.
is it dependent on that?
It's just purely magnets. It's only
Okay.
dependent on the next V in line, a V
Oh,
overlapping a
okay.
V, and
Okay.
you have to remove the bar where the
Okay,
overlap
yeah.
is because it acts
Yeah.
like a brake at that point.
Okay, that's what I was asking for, and they kind of use stuff like that at places that have roller coasters, so to speak.
They can use
But
a electromagnet to turn it on and
yeah,
off to simulate a bar magnet being present
yeah,
and not
yeah.
being there.
Well, and that is really good, and I appreciate you bringing that up. It's not quite what I was getting at. To me, that still is saying that for to do a work, that it is still dependent on something extra to
It's
either
dependent on the magnets.
or to pull. Yes, yes. And so I see the equation there,
Am I too loud?
and so mine is, and you guys can, I would love the correction on it. Mine is interrelated with the vision between the fields and the atmosphere itself. And so that's what I'm trying to get at.
So with the hot copper that you were talking about, was that exhibiting the Meissner effect then, or were you putting the magnet in contact with the copper or something?
No. Well, I've done both. I've actually tried to get the copper to sit on the magnet, and it refused to underneath the conditions that I had. And so actually,
while it was heated.
well, it's just the action that I have the magnets rotating at an RPM that is compared to a linear speed of like Mach 3 to Mach 7.
So this is a dynamic magnetic field that the
Oh,
copper is
okay. So
experiencing.
this is eddy currents then,
Yes,
right?
yes, exactly. And I have found that the eddy currents actually build up with the speed.
Which
Oh
is
yeah.
because it's like
Yeah.
viscosity. It scales with the viscosity of the.
What's the point? What's the point of spinning magnets? Are you trying to build a
Well,
railgun?
no,
You trying to float a
no.
spaceship?
What
What's the point?
no, what I'm doing is I'm building a vehicle. I'm building something for me to ride.
Oh, okay.
Cool.
And so what I actually built a frame that was the size of a Toyota 2 years ago, and put it on put my power unit, as I call it, on it, turn it on, and as soon as it hit the right RPM, it raised it up 3 feet in 2 seconds.
With
Okay, so you got a black box. Hang on.
What's that?
Hang on. Whoa,
The
let's
whole
go back.
vehicle then?
Wait. Let's go back. You got a
Okay.
metal frame, something like a car. You got a
Uh-huh.
black box with some spinny magnets in it. You spun the magnets up and the whole thing levitated?
Yes, sir.
Okay.
Nice.
Well, it must have been a big box with a lot of magnets in it.
No. Actually, it was one magnet. One
How
magnet.
like a giant neodymium one, or just like how big is?
Well, actually, it was the smallest magnet and smallest
Neodymium wouldn't be
neodymium.
appropriate for that.
I'm not going to, I'll tell you what, guys, that the end of next month, I will be glad to present this stuff
All right,
after
well,
I have talked to the
that
ones
just
that
brings
I
up a
have.
couple of very interesting little mechanical problems. Let's say you got I'm just gonna you got a plate 8 inches in diameter. Okay, it's a spinny thing. It's got your magical magnet in it, and it's lifting up whatever 500 pounds of steel, just to give it a number, right? Big metal
Yeah,
box.
sure.
Okay. How are metal plate pushes against something? What, some container box? So
Nope.
no.
No,
So the
it
metal
wasn't.
plate is just
The
the spinny magnet is just
the magnet
spinning in a
wasn't.
box magically all by itself. Nothing's
It
supporting
was
it.
no. It wasn't in a box. It was out. It was exposed to the atmosphere, and
Okay.
and
So
the
there like
magnet.
a pin on the top and a pin on the bottom that keeps it from flying up or down.
It was in a controlled position, and it was rotating. It had 2 different rotational factors to it, and it didn't have any magnet above it or below it, and it didn't have a magnet to the side of it.
Norman, it sounds to me like there's a few details, that could be
That
considered
I'm not
proprietary.
adding
You're
to
leaving
this.
out of this description.
Of
Show us a
course.
nice video when you make
Of
this
course.
presentation.
Of course, I will tell you this: that when a magnet moves and it's moving at enough speed to do this, it disappears from your vision. Can't see it anymore. And that doesn't mean that's not there. It just means that it's going fast enough that I could pick it up probably with a high-speed camera, but I can't pick it up anymore with my eyes. And yeah, there are things here that I'm obviously leaving out that I will
You're saying it
love
develops
to
some
tell
kind of
you guys.
invisibility?
What's that?
It develops some kind of invisibility
Just
cloak around itself?
Well, it's just
just
as it moves.
just
The eyes.
just visually.
You can't see
It-
a bullet either moving, you know. I mean, it's just
It's
it's
just
going real
that
fast.
yeah, when it
No, if you
gets to
have
moving fast enough,
guys, if you have a metal plate and you spin it, I don't give a shit how fast you spin it, it's still going to be visible.
but you're talking about spinning them on place.
So he's
Spinning
saying
in one
magnets radially,
place?
like out at some radius, right?
It has a combination of movements. It's not just sitting and spinning on place. Yeah, if you sit it and spin them on place, yes, you could
It's
see it.
probably,
Oh, okay.
I would guess it's processing. And so if it's spinning really fast, it just looks
So we
kind
got
of
a
blurry.
plate that's
That's what
spinning
he's
on a
describing.
string that's the whole thing
No.
is spinning.
Yeah, Drew,
Well,
he's not saying it's invisible. He's
it-
saying it's kind of like it's spinning so fast that you can't see the.
Yeah, that's fine.
it's
Okay.
doing the same thing as the Earth around the moon,
Yeah,
Is
that's
it a Neil?
processing.
and it's going. It's moving. I had it moving at 26,000 RPM around
Wow.
something else that was moving at that speed.
Cool.
Around
By the
something
way,
else.
Norman, I
Can't wait
put
to
a
see that
link in the
video.
chat to Xeno Astronautics, which is a company in I think they're in New Zealand. So they're actually deploying these things or close to it. They have superconducting magnets that you can use to, when you have a satellite in space, you can have that superconducting magnet interact with the Earth's magnetic field and use that to align the magnet. So you can do, sort of substation keeping.
So
with
the
that
processing
magnet.
that I have it do, I actually have I used the smallest magnet that I had at that time, which was just slightly over 2 inches in diameter.
2 inches is still a significant neodymium magnet, right?
Yeah, it is, and it had, according to the
Drew,
way
I've
they
had one of
measured
those.
it was measured at about 300 pounds full force. The way that they advertised it, not a big one, just the way that it was doing what it was doing.
And this was attached to that vehicle or that.
It was attached to the vehicle. It was free moving. It was permanently attached to the vehicle, but it's free moving.
Right.
It had a motor on it. It's free moving, and as soon as it hit the RPMs, I shut it off because I'm thinking to myself, I don't have control over this thing, and it's moving fast.
Huh. Interesting. And this and this was like over copper, but the copper was at 19, almost at its melting point.
No. The temperature on the magnet itself raises maybe 1 degree Fahrenheit.
But it was near copper and it was producing eddy currents in the copper or something.
Okay, well, this is where we're kind of going to a different technology or a different thought process with the magnet. I have a hole in the magnet, and I joke around. I say the magnet has a black hole inside of it because of the way the magnetic field pulls on it. And so with that, I have it. It's attracted to ferrous. It opposes the copper, and it creates a fight. And as it does that, and it's processing, then it creates its own little world, and they call it a moment of magnetic spin.
Huh. Okay, that's a lot of things to think about.
And I have gathered 7 different laws of physics that this operates from. So when I talk to people, I have to ask them how well they understand the different laws of physics as they combine, because I do what I call creating a circle of 7 laws and the solutions from each one of the laws. have to agree. If they don't, I explode magnets. I bend very thick steel bars in the process. So they all have to agree. But when they agree, we have a magnetic field around the Earth that we never think about, and it's moving all the time. I just have this one moving within that one.
Huh. Interesting. All right.
Can't wait.
Thanks for that.
Oh, thanks for the question.
Hey, Tim, I'm ready to present anytime.
Sorry
Okay.
about that.
Yeah, no, that is
I am
totally
too,
cool.
Tim.
That's
So
okay.
it's, you know what,
I
it's
look forward to your
exactly 6.
presentation, man.
Guys, so why don't we do this? I'll put Richard's hand down for the moment. You know what? John, I think, is ready to hit the road. So everybody, let's give one more applause to John, who I think has already left. I don't even see him.
I'm just getting some coffee.
No,
Anyway.
it's done. It's done.
We're done.
book-
We're done.
The,
Okay.
the
Hey,
book has
great,
retracted
great
you.
meeting you guys. Thank you for listening to my
Stage
stuff.
left.
Thank
John,
you.
thank you so much for
I
presenting
applaud all of
today.
you guys for not throwing any dead cats or anything like that at me.
John, if you cut out now, you're not going to be able to hear about the coolness of a real propulsion system.
Which is that? Oh,
well,
I'm
let
not.
me-
No, I just went and got. I had to excuse myself for a moment, and then
Well, let's
I
go
grabbed
to-
some coffee.
Guys, let's go to Curtis. I want to go to Curtis because Curtis has a presentation for us. He wants to do some updates.
All right, let's hear Curtis' presentation. All right.
You guys, can you see my screen?
I can, yeah.
Yes.
It looks
All
like
right,
this one's a
Curtis.
little more structured. So yeah, I'm gonna mute
Oh.
everybody out, I guess, and then
Curtis, you're raising the bar.
okay, go for it, Curtis.
There's the bar. Wait, is it open bar? Anyway, okay, so I'll give some lab updates for Fullerton, and also like I do every time, I'll have some remarks in physics. So let's see here. Okay, so previously we were reported that we were working on upgrades to the device. This is a slide I've shown before. So as you can see here, we have composite bearings. And the other thing that with this type of build is the bearings are all on one plane. So that has some play to it. So we were working on trying to remove that. So this was this next slide shows kind of the way we were doing it. So on the left there's the mega device with the bearings that are that were the previous, what we were previously using, which is the ball bearing, stainless steel rods. And what we were finding is those were actually scoring the steel eventually, because the thing's vibrating so violently that it would perform great, but then the performance would degrade. So this being essentially a physics, I consider it a physics experiment, and we're trying to prove a Mach effect, that it needs to be repeatable. And that's one of the things that's been haunting this experiment for a while. So on the right here, this is a build with what we call the null device. The null device is meant to show that the effect goes away by having 2 equal masses on either side. So the way this effect is supposed to work has to do with those unequal masses. So you can see here that instead of one plane of support, there's multiple planes of support. So there's what we call these things protruding out where the bearings are in. We call those ears, and each of these has 3 ears. So what we were trying to do is on one side have our ultimate setup is going to have devices that are built such that the masses on either side, one side of them can be swapped from a brass mass to an aluminum plate with ears, so that we have at least 4 supports, so that we constrain the motion to 1 dimension. So that's what's pictured here. So this is more or less complete. I mean, we're still learning. One of the things we did learn, we were excited about these bearings. We were putting 1 on each side. We didn't need that. We just need 1. Also, if the rods are not really perfectly square, the thing will end up binding, right? So what we do with these now is on the aluminum side, we have 1 ear with a bearing, and the other ears are left open, and that still constrains the motion enough that that y-axis problem that we had previously is significantly reduced. So that's right now running. I mean, it's been a couple of iterations to get it to pass what we call the jiggle test, which is when you move it with your hand, the mass is free to move. Previously, it was binding up, so you move it and it would move with it. And so that was kind of giving us strange results. Now, before I go on to show what we're getting now, and of course, like I said, we're barely getting this working. So this is like early stuff. I want to revisit the past. This was when the experiment was in the air on a pendulum. And of course, in the air on a pendulum, you're pushing against the air. So this is a real force. This is a force due to air, okay? And we know that now. We're in the vacuum now, but I just want to revisit this because this kind of informs us what to expect, right? So this is a pendulum. In the vacuum, we have a torsion pendulum. So we do have a similar type of effect because the torsion pendulum does have a C-flex bearing that will restore the pendulum to the center. Okay, so we would expect a similar type of dynamics going on. So this was, as you can see here, the way this behaved when we put a frequency on it, and notice that this frequency was a single 32.8 kilohertz for 5 seconds. It wasn't sweeping, it wasn't doing anything fancy, and it was a sine wave, by the way. Now we're using different waveforms, but it gave us a signal, and that signal still it was a pendulum. So even though it gave it a kick, the pendulum started to sweep. But what happened is that the impulse, you can see that the sine wave that's produced has a offset, right? So that kind of shows that okay, there's an acceleration going on. There's a push. There's an actual force. Okay, so I want to show that to kind of inform like the preliminary results we're getting. So now before I go further in it, this is a sweep over 20 kilohertz, just to kind of characterize the device. And you can see there's a lot going on. Like as we sweep from 44 to 24 kilohertz, we're using a sawtooth wave, a 90% symmetric, 90% up, 10% down. And as it goes through, you see, different behavior through that. And what I'll do after this is I'll go through the videos, and I can show you guys videos of different runs as I step through this. So this was all work that I did yesterday. Now this is the last run of yesterday, and you'll notice something that we haven't seen until this device really running it this way. We haven't seen until that back then when we were running in air with air effects going on. We see a similar type of thing where there's a kick, and you see that kind of envelope motion of the thing settling in with the C-flex bearing, with the kind of pendulum type of wave motion. So what's going on there is that first kick, that was this aqua color. That's the actual device inside of the frame, and the red color here is the actual the frame, which is coupled with the torsion pendulum. So they're like, it's screwed on there, so they move together. So you can see that first the device moves, the springs compress, and then the rest of the torsion pendulum is moved by those springs pretty quickly, right? So you see that kind of that kick, that initial kick, and of course, here I'm having the device sweep. This is a signal that's done over half a second, and basically a sweep through, I think this was 33 kilohertz to 32 kilohertz. And it sweep down and sweep down again, sweep down again. I let it do that for 5 seconds. I paused, another 5 seconds. I did that several times. So you can see here that especially this initial one, there was like a significant kick. Now later on, just out of curiosity, I just did one pulse real quick, and it was like, it went really far, a little bit further than this. So we're getting there where we can narrow down. We're getting close, I think, to narrow down. Okay, where in the frequencies, because every one of these piezo stacks that are built are a little bit different. You got to characterize it. You got to find out what's going on, what frequencies to want, what waveforms to put in there, and there's a lot of interactions. So it's not a straightforward thing. Now, looking at one of the people in the group was the one that emailed that previous picture of what we used to do years ago. And that reminded me that, hey, we used to run a constant frequency right where we thought the resonance was. So that's something we might want to do is pulses. So that's something that, like I said, this was done yesterday. It's been raining. I am not in the lab today. It's raining down here in Southern California, so I stayed home. But yeah, we're really excited and looking forward to this, because this device is solving a lot of the problems we had in the past with the bearings and repeatability. As you can see here, the device is very repeatable. Every run, it performs within a similar envelope. Okay, so what I'd like to do next is show you guys some videos of these recent runs. So, oops, minimized. Okay, there we go. Okay, so this first run was a sweep over 37 to 32 kilohertz. And like I said, one thing I want to point out is on the bottom left is basically a fast Fourier transform of the signal that's being put in, and also there's a reactive component from the energies coming back from the piezo stack. And you can see there's a lot of sidebands that happen when the action happens, that the thing, instead of having fixed peaks of all the harmonics, that all these sidebands will appear. And that's kind of what we're thinking that we're after to get this performance. So you can see here over that range, it looks like there was something there. And then what I did after that is I went ahead and said, okay, well, 37, 32, I swept from, at first I said, okay, I'm using the same sweep rate. So if basically this is 2 kilohertz per second. And so here I'm doing 37 and 36, and you can see there, as expected, there's not much going on. And then I did 36 to 35, and you'll see that this is getting closer to the resonance, and you can see the envelope has a little bit of that signature of the interacting with the pendulum. And as I keep going down, let's see, where is 30? There's 8. Oh, there's 9. 34 to 33. And that has a little bit of that. And you can see, oh, so by the way, on the top left, that gold color trace is a accelerometer basically getting squished in there. So the higher that peak, that means there's a lot of motion. The red trace is the actual motion of the device measured on the other end of the torsion pendulum. And the blue is basically the power, the rectified power that's put in. And this is the last run. This is the run that I showed that analysis of. So you'll see that in real time here. And I can actually, what I should probably do is go ahead and put it at a quarter speed and start it from the beginning, because that first run is the one that's the most, you can see the most motion. So you can see the sidebands kind of kick in and out as it moves, and there's that the red trace going down as the pendulum is or the torsion pendulum is doing its thing and recentering. So it looks like there's a real kick there. We got to be able to repeat this and get that frequency dialed in for each of these, get them characterized. So let me go ahead and redo this there. Okay. So next I want to bring up something. I think I emailed him. I don't know if he caught this, but I decided in this talk that I would kind of I've given several talks in Sax's theory, and and the last presentation I gave was talking about symmetries in physics. And so I thought about it, and I thought, you know what, I gotta, and there was a reason why I had renewed interest after decades of going back and looking at that theory. and exploring it again. And so I'm going to cover that here. So basically, you know, as you guys know, if you've seen my talks before, you know, I'm the kind of guy that when I do physics, I like to look at what's fundamental, start from first principles, and try to figure out what those are, right? I got to be honest with myself, you know, what I know, right? Being human, what I can figure out, what I can understand, that's what's important to me, right? So this is a you know, kind of a short list of the things that I've talked about before. Matter, we know now, has a wave nature, right? That's pretty clear. When we discuss these things about UFOs and things going through matter and, you know, us being not able to understand it, part of it has to do with us, the way we're conceiving of matter as being something solid, which we know it's not, okay? You know, a few, I think in December, I brought up Carver Mead's presentation. You know, you can do a neutron diffraction experiment, right? Neutrons will diffract, right? Neutrons, right? Which normally you think of like at a fundamental level as like a little billiard ball, right? And that's a simplified model, but neutrons have a wave nature, okay? So everything, matter is waves. And so when we talk about things going in and out of each other, like, you know, having some matter that we think is solid, it's, you know, there's nothing about matter is solid, right? You know, Mach's principle, periovulation, this is the key thing here to me, because periovulation was confirmed in 56. Okay, so that's something I covered last in the presentation I did 2 weeks ago, where on the small scale, right, and it was kind of ironic and sad that the year after Einstein, you know, after Einstein passed away, that's when it was discovered, periovulation. Okay, so you know, I don't know if he would have gone back and done what Sachs did and redo his theory based on that, but you know, that's significant. Okay, periovulation in space, and then later it's confirmed with time parity is violated, and some can argue that, you know, that's on the small scale. So let's, you know, the other of these are not that controversial. Noether's theorem, general covariance, correspondence principle, those are standard things we do in physics. So I'm going to focus on the parity violation and the large scale, what I'm calling the large scale discovery of parity violation. So this was something that, thanks to the pandemic, I had more time to pay attention to cosmology. And there's a YouTube channel called Cosmology Talks. I highly recommend it. They're really good kind of interactive presentations of papers. And I've listed here 3 papers that actually go over a parity violation. And the last one was done recently, and which is a really good paper because it shows that, okay, you know, general relativity can predict some parity violations, but not all of it that's observed. So it's kind of interesting. So the fact that parity violation was found in the large scale is what led me back to think, okay, maybe Sachs was right about getting rid of space and time symmetry when he reformulated general relativity with quaternions/spinors, whatever you want to call that mathematical structure. So this is the fundamental reason why I got renewed interest. Okay, so I really haven't talked about this before. I was kind of leading that way in the past, but if anyone's was ever wondering why why would Curtis do that, you know, whatever, this is the reason. And like I said, I mean, there's the archive links. I'll send Tim my presentation, and you guys can get those links on the website eventually, I think. But and you can also look for these on YouTube. There's talks, like I said, on this on YouTube, and that might be the best way to go. But so the question then, you know, like I said, if you go back, if you haven't seen my talks, you might want to, if you think that, okay, now that we know there's parity violation, and guess what? The guys back then, you know, 100 years ago, when they were thinking about this stuff, they thought space and time reflection symmetry was a law, you know, basically it wasn't violated. They included that in their theories. And we know now that that's not the case. So, you know, maybe thinking about the way they were working on this, like, and here's an example slide of, this is a really nice talk that Tiziano sent me months ago. Einstein when he was, figuring out the metric tensor and decided on, what he was going to do for GR. You notice the quote on the bottom, okay? So basically he wasn't looking at this as a geometry, right? It's a description. He was moving more towards the field theory, okay? And so that's where we ended up. So yeah, those are my comments, and let me know if you guys have any questions and about the what's in the lab and the talks I've done in this discussion here.
Curtis, thank you, man. Thank you. So let me see. You know what? I want to put this thing on gallery view. I'll open up. Folks can unmute themselves, all that kind of stuff. But let's give Curtis an enormous applause. Curtis, thank you, sir. And again, this is super casual, so usually we don't even applaud during the mellow sessions. But thank you for bringing these, and thank you to John as well. So let me see. Richard has had his hand up for a while. Richard, go for it, sir. Oops. Let me ask you to unmute. Richard L. And he has his hand. There we go.
Okay. Can you hear me?
Yeah.
Oh, okay, great. Yeah, so for Curtis, I actually put something together that is a pure mass. It's driven by a motor, and it actually has instant response in a positive direction. And it actually confirms a lot of what you guys are working on there. But what I would like to do is send you a video so you could take a look at what it does. And, there's a lot of specifics in it when you start to break it down, but it would surprise you because I'm looking at how you guys are approaching that project there. And then I'm looking at what I did and I go, wow, this thing would answer a ton of questions. And it would confirm a lot of the theories that you're going on about there. Anyway, could you hear me?
Yes. Yeah. Yeah. I think.
Okay.
I think Tim can coordinate with the communication, right, Tim? You can have.
Yeah. Yeah. And I would say, Richard, if you want to maybe just drop your email into chat and he could work out that way, and then Curtis, if you want to drop yours into chat also. I mean, that's the absolute easiest way.
There you go.
Yeah, there we go. Thanks, Curtis.
Yeah, and actually we had a
How do I
group
do
meeting.
that?
We had a group meeting yesterday, and one of the things that we brought up is that we should probably be looking for other ways that the Mach effect can be proven or done or used. So that's something that I'm on the lookout for. I mean, I did notice that Gravel Flyer had some similar elements, right? A piezo thing, a lot of energy going on. So yeah, definitely.
Yeah, I see some of those effects too. Yeah.
And cross-pollinate.
Okay, so how would I drop the email in there?
Oh, if you go into chat, just type your email and what that does is that keeps it off the open internet.
Oh, okay. Go into chat here.
Yeah, because we don't upload these notes. I try and keep any, especially typed versions. I try and keep those off the open internet because there are a lot of spammers and scammers out there. So. But yeah, this gives me the opportunity to do my lecture on cross-pollination.
So I can just type it in.
Yes.
Yeah. Just type it in and hit enter. And if folks save that, and in fact, I'll save that now. You guys can save the chat. There's 3 little dots on that meeting chat. You can save that, but it's not going up on the internet, and that way it keeps emails out so that they don't get stolen and misused.
I'm hoping next time I'll have a better report on the results. But it's slow going. But we're still working at it.
Yeah. Well, no, it's awesome, and it's good to have you guys talk. I mean, you know, we're a really small community, right? And at the end of the day, all we have is each other. So.
Hey, Tim.
Yeah.
It's Brendan. I was wondering,
Oh yeah.
Okay,
Hey,
I think
man.
it went in there.
I had a
Oh yeah.
presentation, and I was wondering if you'd want me maybe try giving that today or at a different one, or
Yeah, no, Brendan, go for it, man. Go for it.
Okay.
Yeah,
Let her
and
rip.
actually, Richard,
if you guys
do
want to
not
close
see
out
it.
Curtis's properly, I don't want to get in the way of anybody.
Oh yeah, okay. Maybe you didn't hit enter, but you know, it's no big deal. The other thing you could do, Richard, is just write down Curtis. It's the CurtisHorn@mac.com. If you know,
Okay,
and
so
then
Curtis.
yeah, it's just first name, last name at mac.com. Yeah, and then
first
I
name,
guess
last name, and then mac.com. Okay.
yeah, just CurtisHorn@mac.com.
I got a 15-minute video if you guys want to see it.
All I see is your hair right now, Mike.
Okay, and then
there we go.
Okay, so can you hear me okay?
Yeah.
Oh, you can. Okay. So yeah, that's the only question I had. I would just I would like you guys to give it a professional look at it too. And then maybe we can get into all the specifics. There's quite a bit of stuff that goes on there. It's interesting.
Okay. But you don't have that ready today, right? So maybe in the future we'll come back to it, or were you going to send that over?
Well, if I can get a video, yeah, if I can get a video to Curtis,
okay,
it's in my phone, so yeah, I would have to, yeah,
well,
unless you had a phone number, I could send you a video right away. But
yeah, let me go to Brendan then. I think Brendan wanted to present on something, so let me do that. I think that we're all squared away. So Curtis, thank you again, man. I'm gonna jump right into Brendan's presentation. Here, Brendan, I'll spotlight you, and
oh no spotlight, no pressure.
Spotlight, you busted. You busted. Okay.
Busted for having interesting ideas.
That's right. Plant busted.
Well, I've given a few public talks before, but for some reason I've got like butterflies right now just because of the intensity sometimes around here. And dude, I know you guys are really smart scientists.
We're off the mellow scale today. So
yeah. I just disclaimer, I'm not a scientist. I'm not a practicing scientist. I'm not a mathematician or anything. I'm just call me a surveyor and a philosopher, and just very interested in the progress of humanity. And I'm really interested in meeting aliens, like for real. So I'll start there. So let me share my screen. In that vein, I've done this little thing up, and make sure I'm sharing my right. I don't want to make the same mistake as last time. Can you guys see this?
Yeah. Nope, it is good. And I'm recording.
Cool,
so
cool.
I think, yeah, we're all set, man.
Okay. Now, so in order to not have my headphones automatically go off, I'm gonna undo my headphones, so I might not be able to hear you guys if you say anything. But this is so I've always wanted to meet an alien. I think like when I was a kid, I wasn't raised with Star Wars at first, but I was like about 10. And so of course, the first thing I do when I go and see that as a kid is afterward, I went to the library and ran a search for interstellar travel practical application. So I was like, how do we do this? And fortunately at the time, I don't know if, I think Alcubierre had come out with his version of the warp drive already, but it wasn't super popular and there weren't a lot of people talking about it yet, or at least it wasn't in my library. And not having the internet at the time, that was my source. But lamentably, the only real piece I found that treated it sort of seriously was a book on solar sails. So, you know, as some here may know, that doesn't really suffice that well. and you'll see why. So, you know, we have a lot of, forgive me if this is review for like most of you, but we have the challenges of interstellar travel. And for starters, space is big, like really, really, really big. Yeah. And how big is it? It's so honestly so big we don't even bother measuring the distance itself. What do we measure instead? You know, light and time. We measure the amount of time it takes for light to get across the space at 186,000 miles per second. I believe that's 300,000 kilometers per second. You guys know all of this. I made this for kind of a broad spectrum audience because I feel like sometimes we get a little bit insulated into our little bubbles and speaking our lingo. And from outside perspectives, I try to share this stuff with my friends and family that are frankly normies, and they're like, what are you even talking about? So trying to normalize it here. So yeah, at 4.396 light years away, the closest star would take 4 years at that speed, and that speed's not an option conventionally, because you can't get to light speed. Currently, the world's fastest rocket would take about 30,000 years to get there. So we need a better way. We have the conventional approaches, which pretty much amount to, minus present company included in some cases, the propulsion methods are generally ion or plasma propulsion through some sort of nuclear power, either fission or fusion. I mean, this can refer to the energy source, or in some cases, the actual propulsion, fusion or fission reaction, or solar sails, which are designed to catch a ride on a sunbeam or a laser, powerful lasers docked at home or on the moon or something like that. And generally speaking, these are both, you know, still impractical, still much faster than rockets, but still extremely slow. And generally speaking, we wouldn't see results from these for some time. And humans, as of right now, like you couldn't put a human vessel on a solar sail. It's the surface area for the solar sail compared to the mass it can transport is huge. They're vastly different. And so you couldn't really think of that as a way to transport people. And ionic or plasma to do those distances, the amount of fuel you're talking about is obscene. And more the closer you get to light, you know, the closer you get to the speed of light, as some may know here. And then few people have proposed exotic solutions, which are still within the realm of understanding and sort of conventional, which is antimatter and photon explosion propulsion, you know, and a big bell behind the craft, possibly some kind of pusher plate. And then I add as a caveat to the list here, the Orion project, if anybody knows about that, which is, you know, he designed a whole system to drop nuclear bombs behind the craft, and that would supposedly use up the supply of nuclear bombs on the planet, and or, you know, to defuse the situation, no pun intended. And instead, as we know, they opted with chemical rockets. As some may not know, it's, you know, it happens that that system can deliver a nuclear payload. So they're like, hey, win-win. And as some may know, that, you know, NASA was, a lot of the beginning officials in NASA were brought over from Operation Paperclip. So a lot of crossover there. No shade. Might want to work there at some point, so I won't get political. These are still slow. And you know, so you still have this problem of massive delays in time. So a few ways to deal with this: generation ships. If human lifespans won't make the trip. Breed. There's a few ethical concerns there, like how do you get a whole population of people that have left the planet and left all forms of government and adopted, basically been born into kind of a crappy situation, like you're all stuck on like sardines on a moving tin can to another planet. So you have to have like an almost religious, you know, conviction to the cause. And you know, as we know on Earth, that humans are very human and don't respond well to authority for very long. And so those are the issues there. Cryogenic freezing, you see this a lot in sci-fi, put them to sleep. and genetic arcs, print humans on the other side from raw material. I believe that Avi Loeb was talking about something like this in extraterrestrial, in combination with the next stuff, which is robotic probes, send only automated machines, which could make more machines for themselves, as we know with von Neumann probes, or possibly be the ones that print out the humans or other life. Of course, like you may notice a few of these on the list are nowhere near confirmed, but you still mention them here because they're closer to canon. So, as you might know, none of them are very good, and a lot of them don't involve with any of us going or to meet the aliens or getting there in our own lifetime. The best some of them do is maybe you'd have signals sent from automated probes that basically have powerful AI that can manage to move around on the alien surface and do stuff mostly for themselves. And if any of them break, you're out of luck, right? And you don't get your pictures sent home. No ET phone home. Also, here's a little caveat. Einstein's sitting there like the soup Nazi, except it's FTL Nazi. He says, no light speed for you. You can't reach or exceed light speed conventionally. We'll look at those other options. And because the relationship between speed of light, matter, and energy being very fixed, and that E equals mc squared, the faster you go, the more energy you have, therefore the more the mass. I might be butchering that, but long story short, you just can't get there. There's no amount of fuel in the universe that could get you to light speed, maybe some fraction of it, but then any acceleration past that, you're just talking about more and more and more and more fuel that you have to add in. So that's extremely impractical, because as we know, weight has a lot to do with space travel. Weight being less is a good thing. So we come to FTL solutions. We've got warp drives and wormholes, which are basically, I think of these as two sides of the same coin, because they both involve entanglement to some degree, and they're both a warp in the fabric of space-time. Just that, the warp drive, it moves fast, quote unquote, faster than light, but that's because it's moving space-time. And so that's how it gets around this, the light speed Nazi. Or I hope this doesn't get demonetized on YouTube for me saying the N-word too many times, that N-word. And then it has near instantaneous travel relative to a static reference point. Some examples of this would be the antimatter powered warp drive from Star Trek, and that's a fictional reference, pretty much the only fictional reference I know of. But it starts to become more realistic with the Alcubierre drive, which we talk about a lot. Well, that calls for a lot of exotic energy, and basically a huge ring made of almost exclusively exotic energy, and that amount of energy somewhere close on the order of like universal levels, and so very impractical. But at least he gave us the theory and the equation and started us on this path. He's like, okay, it could exist theoretically in the mathematics of the universe. Not that it's practical, but kicks the can down the road. Then you have, other examples like Sal Pais's FTL drive, Jack Sarfati's, both of which are theoretical, but both of which move the ball forward, right? Lower the energy requirements and get it within closer to the range of what we could theoretically do. And you imagine this process, it's no longer like a theoretical problem, it's an engineering. And on the other side of the coin, we have wormholes, which are theoretically plausible. We haven't seen one yet. We're working on that. And this is the idea that there's a hole in space-time, basically 2 points bridged between entangled points around black holes and other areas of extreme gravitation, extremely high energy. This involves instantaneous travel because the destination and origin are so entangled, they're basically the same place. They become the same, whatever way you want to look at it. This exists in fiction in a few different places like Stargate, Wrinkle in Time, which that has more to do with mental travel, but still technically a wormhole that they're using, basically kicking up an old wormhole. Another one I would say here is maybe Sliders, if anybody remembers that. But and I put here the Star Trek Spore Drive, which is that's in Star Trek Discovery. But how they're doing that is that they've discovered some sort of interdimensional or hyperdimensional mycelia network. Paul Stamets, the namesake of who's the namesake of the character on the show that invents this thing, we find this hyperdimensional mycelial network, and they're basically dialing through it like an internet, and finding locations of certain resonance in space-time and just engaging that and popping through. They use like a giant mutant tardigrade, yeah, that's about right, to navigate through this system that's basically like hyperdimensional extension of our local dimensional network of life. And that's just one of the most far out concepts I've ever heard of. I'm quite a fan of that one. You'll see that like where I lean is a little bit more in those directions. But and then we have at least one attempt to make this really, which is counterportation. I'm still working on understanding this, but basically it's using a quantum computer to draw up a theoretical model of a wormhole and the way that it transports qubits between two locations. Like they're using qubits to model an entangled photon between two locations, and thereby like doing this through quantum computers, they're able to possibly generate a wormhole between quantum computers and using that to model and possibly project entanglement with distant photons. Again, that is super complicated, but that's on the horizon. Pretty cool stuff going there. Here's a brief go through with the QBA drive. Utilizes space-time compression and expansion to enable faster than light travel. Its warp bubble bends space-time around it, removing it from the effects of inertia, so it gets over that light speed limit, and it travels in an envelope, basically. Theoretically operates within general relativity laws, but it requires this insane amount of negative energy or mass, which, as far as we know, we haven't seen it, we haven't discovered it, we haven't created it in the lab. But there's more to come in terms of ways to negate the need for negative energy. So yeah, the energy requirement's insanely high. So we have Sal Pais, who is this he's a pretty brilliant guy, and he wrote the Superforce paper, which is related, but he also put out these Navy patents that were the talk of the town on the internet for a bit, still are. People wondering if this was like, a released patents for an actual working UFO, but no. There's debate over why he did this and why they released this way. Maybe just to say, hey, we know that we at least know that something like a Tic Tac could exist and maybe do these sorts of things based on what we know. There's some factionalism in the Defense Department as far as some, like the Air Force, for example, has demonstrated pretty clear track record of trying to suppress a lot of stuff and using obfuscation and disputing the Roswell crash by putting out a fake story of Mogul that came years later. But I digress. It uses it controls charged matter with vibration and spin for fusion containment. Uses microwave emitters on pockets of xenon gas, convert that to asymmetric plasma, it's made to plasma, and then they make it asymmetrical through applying various frequencies, some of which might be terahertz frequencies, and that creates gravity waves, and those gravity waves are controlled through a waveguide here. It achieves enough energy densities for space-time warpage or polarizing the vacuum if you're using Hal Puthoff's framework. And that propulsion pretty closely matches the observables for UFO phenomena by moving around so fast and violating, a lot of what we know about inertia and physical movement in these objects that we're seeing. So he emphasizes that his approach, he's very fond of saying, this isn't new physics, it's new engineering. So it's a new perspective on old physics. Jack Sarfati, who we know and love, he's offering to change the value of C in a vacuum by changing the electric permittivity and magnetic permeability, sorry, that exist, epsilon and mu, that exist in various metamaterials. So that allows him to engineer the space-time metric with way lower power requirement, because in a sense that's like being front-loaded into the materials, or that your energy is in the material engineering to get those just right. Your energy control, energy information, tension, to order these materials in such a way that they're so dense, or they such a crazy refractory index that it changes C. So that predicts redshifting from high gravity on the leading edge. So in front of the craft, there's gravity, which is pulling it forward, and that would create redshifting, observable in some cases, and blue shifting on the trailing edge, which is sort of, some might call anti-gravity, or you could say negative gravity, or you could say negative space-time curvature, or negative energy, all AKAs. So and if you wanted to use the analogy of a black hole, front is a black hole, back is a white hole, or that sort of thing. So red equals gravity, positive curvature, space contraction, time expansion. Blue is anti-gravity, negative curvature, space expansion, time contraction. We have some other warp drive models. This guy named Notario came up with a way to lower the exotic matter and energy requirements by just simplifying the bubble geometry. So still we need some exotic matter possibly, but like less. And it's another tweak done to the math to bring it closer in. I know at least one of you guys in attendance, Todd, shout out here about your warp drive paper from Maxwell's equations, which I plugged into GPT at one point and wrote a different paper with in honor of this, because it seems very simple and intuitive, even though it's insanely complicated. They don't really fully understand it yet, but you done good there. And quantized inertia, which you talked to Mike McCullough at the last APEC, and it's not, I don't think he's going around saying it's a warp drive. It's not technically a warp drive, but it's neutralizing inertia. It's possibly one way to play with inertia and or dampen inertia, and that's one way to allow for light speed travel, because you can get around the light speed guy, the light speed cop. So you also have Yuri Oroshenko, who wrote a paper about how to use a spherical warp bubble to escape black hole. And you also have Casimir warp drive by Fernando Loop. And this one's interesting. Harold Sunny White, who has a fan base out there, he's talking about nanoscribing metamaterials in certain shapes that at a nanomolecular level create or foster Casimir cavities in 3D printed material. And I saw a different paper that was talking about using AI to possibly generate these cavities. So if you're talking about an AI that's generating optimal Casimir creating nanocavities, that it could possibly collectively warp space-time that's pretty insane. You're basically talking about like the living conscious ships that are nano producing themselves. That's pretty major. And then you have Hal Puthoff, who's done some work on creating a warp drive on his premise of polarizable vacuum. And so if space-time is actually a polarizable vacuum, then that means that you can polarize it. You can create gradients of energy on it that allow for you to warp space-time. And to an extent, I think that the Biefeld-Brown effect sort of does this. Maybe that helps go with that to help explain possibly what's going on when they have asymmetrical capacitance in those experiments. So when we get to wormholes, which are awesome, but here specifically, I wanted to mention this ER equals EPR thing, which is so Einstein and Rosen in 1935 showed that two black holes at significant distance can be connected by a tunnel through space-time, a wormhole. But later on, Einstein, Podolsky, and Rosen so Susskind and Maldacena got together and made this new interpretation on wormholes where they asserted that two entangled particles could be connected the same way and that those represent a wormhole as well. And that's over Einstein, Podolsky, and Rosen. That's called Einstein, Podolsky, Rosen. So the conjecture is the ER equals EPR conjecture. And it turns out that modeling wormholes turns out to be a super useful application for quantum computers. And that's the thing, believe it or not, is finding like, hey, we have these quantum computers now. What do we do with them? This sort of leads me to believe that possibly that complex nanocircuitry, either in conventional or quantum computers, entangled qubits and so forth, could and or the human mind could be entangled with micro wormholes. Maybe this is some sort of facet of reality that maybe nature has been doing this since nature tends to be it's been at the game longer. I'm not maybe intentional or not that we understand that there's a fabric to reality and that certain things exist, then it's possible or at least conceivable that the oldest engineer we know of is already doing these things. And that leads to some other parts of this. Some truly odd solutions. Now, remember here, before I go into this part, we're talking about, solving a problem, and the problem being, how do we meet aliens? Okay, so not all of these might be quote unquote going to other planets, but they might just as easily involve meeting aliens. I wanted to bring up a quote from Einstein. He says, if I had an hour to solve a problem, I'd spend 55 minutes thinking about the problem and only 5 minutes thinking about solutions. So, that's important because a lot of the times when we're trying to fix something, we just start going about doing it or doing solutions, jump to solutions. Let's define the problem. A lot of us get into this kind of work or this kind of thinking and go and get physics degrees. Sometimes you go to other planets, but do you really want to go to a dead planet? I think a lot of people actually want to meet aliens. That's where the excitement comes from. Like, are we alone? And so it leads to these other solutions. People talk about mental travel. It's almost a naughty word in science circles, but talk about remote viewing, astral projection. But it has to be mentioned because there's precedent for this in sci-fi too. As this is going on, as Dune is really popular. So this would be transcendental meditation on steroids, basically assisted by entangled micro wormholes or possibly being engineered and or altered states of consciousness, electron spin resonance changes generated in the molecular circuitry of the biological brain. We have as examples the Dune navigators, Wrinkle in Time. They're basically creating tesseracts, their brains, if you could call them brains, or minds is probably more accurate, since like some of them are literally stars incarnated human. And astral projection, remote viewing, which aren't as far-fetched as you might think and have some at least tracking there in culture. So you have the idea of computer simulations, specifically like quantum enhanced computer simulations. You have we have Sora coming out soon. We have the ability to generate whole worlds through some combination of generative AI, quantum computation, possibly entangled photons, taking basically the information we get from distant worlds and what we know to run projected simulations on things. And is there a point if quantum computers are going through the whole gambit to possibly get some answers right, or pretty dang near to right, or spooky right? And how do we check that? And so we could possibly project super hyper realistic, perhaps accurate simulations of alien worlds, just as good as the real thing, given that depends on superposition as it goes through many worlds and potential possibilities, which I think works a lot like the infinite improbability drive of Hitchhiker's Guide, which for some reason didn't make it into this. I don't know why. I forgot, but that goes through all potential probabilities, infinite improbabilities, and finds the right route. So these things could be helpful. And then you have entangled communication or projection. If we were to unlock entangled communication, we may find, it's like turning on an internet and basically sharing multidimensional broadband experiences. I wrote gravity boats here, but I misinterpreted, but Ray Chow, I'll bring it up later. So is it possible that, we see these ETs, we see UFOs, we see sometimes just entities, and there's all sorts of experiences like that. Is it possible that at least some of the beings we conjecture or believe are visiting the Earth are doing so using any of these mechanisms? And that it might not be as far-fetched as we think. If a big wormhole is the same as a small wormhole, we could have billions of small wormholes in the brain, trillions even, on some level or another. And so we have altered states of mental travel. So Terence McKenna talked about the effect of a given psychedelic molecule such as DMT or psilocybin to his wording was a disc into a jukebox of the nanomolecular circuitry of the brain. I'm not sure if that was possibly DNA, and that changes the electron spin resonance of what's going on in the brain. Pretty sure that's hyper speculation, but it resonated with me a long time ago. And we have Jeremy Narby, who wrote this book called The Cosmic Serpent. That's about ayahuasca shamans. And one of the things that happened there was that they were able to, seemingly to draw organelles from inside of a cell when they were able to do these sessions. And over years and years of doing these sessions, they made all these paintings of their visualizations. And Narby gave a friend of his who's a microbiologist some of these pictures. So, oh, this is a certain phase of mitosis or something. That's worth looking into. We have idealists like Bernardo Castro, Don Hoffman, Rupert Sheldrake, Chris Langan, Roger Penrose. I'm not sure if I'd call Roger a full-blown idealist as much as the others. He's still respectable in some circles. And they all sort of more or less hypothesize that consciousness might be primary, at least closer to the fundamental laws of the universe than just an emergent property of complex computation of biological systems, aka the brain. I'm not sure if Penrose goes as far as this, but they all are talking about something like that. This is a link to a really cool Stuart Hameroff presentation where he's going off about the work of Roger Penrose and others in this space. And he was mentioning that the microtubules in neurons act like light receptors. And in fact, one guy said something like perfect light receptors. And they possess some quantum properties, possibly even quantum entanglement with other other parts of the brain, other microtubules to go faster than light within the brain. And that was related to Penrose's work. They might possess some quantum properties that have implications on the nature of consciousness. Might even help solve the free energy principle. The free energy principle of consciousness, Carl Friston, might be something like that. In religion, you have some instances of something like this actually coming up in a lot of religions. In the Hebrew Bible and the Torah, there's reference to rabbis doing this thing called kefitzat hadarek, which allowed them to transfer their mind, or they would say to project. I believe that a few of them allegedly went and projected into the emperor's chamber, the emperor of Rome, which I believe might have been Nero at the time, and sort of harassed him as ghosts. Could be stories, but there's also reference to that in the Quran as well. They refer to it as Te al-Ard, yeah, and that translates to something like earth underfoot, which seems to indicate there's a movement of the medium rather than the individual, and so there's some reference frame shifting, but that reminds me instantly of some sort of understanding of like a warp, as we talk about. Then there's references to Indian yogis over the course of history being able to project into multiple places, or remote view various places. And then, we have reference to the CIA and parts of the DoD literally looking into remote viewing, as many may know, and they weren't, it turns out it's not as crazy as they think. There's some instances of them being quite right. And so fictionally, we have reference, though, as I mentioned before, to Dune, which, you have the navigators, the Bene Gesserit, Kwisatz Haderach, the one who can be places at once, which, I'll bring your attention to how much this looks like this. Kwisatz Haderach, Kwisatz Haderach is Frank Herbert trying to tell something? Possibly. But I think that when I might need to double check and look this up, but I heard recently that Paul Stamets in his relative youth was working with Frank Herbert, the writer of Dune. So full circle there, possibly. And a lot of this is deeply subjective. That's the problem. At least when you're using mental travel, remote viewing, it's kind of like in the UFO circles, it's like the equivalent of trust me, bro. And so there's got to be some way that we can, use techniques, gather huge groups to intentionally do this together, double check their results in a double blind comparison later on, and see, if we can get any objective verification and train that. Now we have brain computer interfaces. So like recently there was a mention of the paralyzed man that was able to use a computer, and that's a thing we have now. So there's the possibility on the horizon, just as easily as any of these other things, to record a remote viewing session directly and see whether or not it was accurate. And we also have the emergence of simulations, and some might be like, I want to go, I want to really go, I want it to be real. And well, what is that? Let's make sure we define what that is. And very soon we're going to be asking questions about more and more about what that is. So we already have hyper realistic 3D VR simulations. That's not hard. We already have generative AI visualizations, which is through the images, which I use a lot of. This is made in Midjourney. All these are made in Midjourney, by the way. All of my images, these powerful visualizations, which are capable of taking commands and generating hypothetical worlds, and side-by-side comparisons of various versions of those worlds, which it may not be, but it sounds a whole lot like many worlds. So those going together, and we have a convergence with the ability to do hypothetical world branching, and that means you could get a computer to go backward in time, in the sense that, like, well, peel back the onion and go back 65 million years. One of the things you could do is, like, okay, run a simulation of what would evolve, if the asteroid that killed the dinosaurs never did that, and they were able, like the protons are able to evolve into super complex humanoids, or go even further back, the Cambrian, and what if something different happened there? Any number of branching possibilities of the various ways that this planet Earth could evolve aliens. And it makes you wonder, actually, if some of the aliens we see are, since they're humanoid, people say, oh well, how could aliens from all these stars be humanoid happened here? What if humanoid is a really handy body plan for other places, but also for here? And it might seem more likely that we might be seeing, if we're in a simulation, we might be seeing simulated visitors from other adjacent simulations, or if it's real, we might be able to see other visitors from alter Earths, and that might be something that aliens decide might be one of the answers for the Fermi paradox. They realize at a certain point they're going to find more versions of Earth that are closer to their biology and closer to their parameters, but still alien, close to home. And that's, FTL is one of the byproducts of FTL might be backward time travel. So it would seem to make sense. And I think Dan Davis, if they throw him under the bus here, no, he's brilliant. But his multiverse / warp drive talks about that. He leans heavy on the mini world side of things. It's possibly directly related to how you're going to get to somewhere else in this world. But I would say, like, you just as easily explore other Earths. Still alien. This is all brought much closer to full circle with Neuralink and brain-computer interfaces, which can, they're possibly getting input and feedback into the system to make the generation, possibly even using part of your own brain to make the generations go faster, get closer to what you want to visualize in these simulations, and making them more realistic, so you could actually be there, maybe even inhabit the body of one of these aliens or something. You got it directly wired into the brainstem. And quantum computers, so they superposition the problem going through the many worlds. And once we get these plugged into our generative AI and our VR systems, how much more likely is it that those results computations will be accurate compared to a classical computer's ability to do so? Then in addition to quantum computers being plugged into the AI, we have the possibility of new age analog computers, which run differently, I think, to get truly random data, and those are going to help out AI, as well as these dedicated language processors, which might be able to translate alien languages in real time into the actual impulses for your brain. So it might not even be quantum simulations, or sorry, it might not even be classical simulations or quantum simulations. It could be black hole simulations. Like, if we get far enough into modifying gravity to produce our own micro wormholes or micro black holes, we might be able to run sims on those, because of the necessity for info conservation, which is something Hawking talked about. And that was the fact that because you need to conserve the information, possibly there's some sort of simulation coded, or the surface of a spinning black hole is coated with informational hair, which is necessary to that could possibly, like a hard drive basically is in terms of a bit, which is either vertical or horizontal. Those are kind of like the hair of a hard drive. These could code information and possibly code for an entire holographic civilization. That might be what we're living in, and or nest in a nested situation of black hole simulations. And in this case, with so many simulations running around and so many people running around between into out of simulations, who are the observers, and is it possible that different simulated / simulating worlds connect? Is there a point where you have all these quantum powered entangled simulations and nested dolls? Is there bleed through effects like that we sometimes accidentally see the simulators as these aliens, or vice versa? If we did it ourselves, is there some potential for connection as more than just NPC to PC? Like if you're playing something like The Sims, if you ever wonder, like, are they aware of what's going on here? Just like how we are, like, is this a simulation? You imagine the sim characters are thinking the same thing. And that leads us to the inevitable question, what is reality in this context? Is this reality being simulated? Or if this reality can be simulated, what does that tell us about reality? And we have to ask these questions more and more as generative AI gets deeper into the rabbit hole of being able to produce video and mimic reality. And what does it say to us? It's similar to how these LLMs are now. I'm not saying they are conscious, but they have been brought about plenty of conversations as to if they are conscious, and that in and of itself says something. If we're so close to actually simulating reality, what does that tell us about reality? And is the basis of experience consciousness? So before we ask, is the base of space-time or the base of reality consciousness? We know that, as far as we know, the basis of experience is consciousness. And that is the hard problem of consciousness, why we need to deal with consciousness. We can't just leave it on the side, because we all have an experience of being conscious. And we get to the possibly entangled internet of experience. Before I go down here, another sidetrack to this is the movie. I don't know if anybody's seen Fantastic Planet, where you have those giant blue aliens, and it turns out that their whole civilization is bent around meditation, which is using this advanced technology to take their souls and basically astrally project to this other planet up in the sky, up in this moon, basically to dance with other ETs that are doing the exact same thing to where they are. And that's like the goal of their civ. And the humans who survived a nuclear explosion, these little tiny people, messed that up by getting a hold of the rockets and going there and blowing up their dance. And that was like really deadly to them, because maybe at a certain point, that's how you thrive and survive and spread your informational seed throughout the galaxy, or galaxies, by doing these things. So with that in mind, there may be this sea of experiences and stuff all around us that are happening we can't even really shake a stick at yet. So matter may be very hard to move across space-time, but data is easy. And it takes a lot of energy to open up a wormhole or a warp drive or a warp bubble for a big spaceship, but not that much energy to open up really tiny areas. And what is all of this except a bunch of really tiny areas? So entangled communication might not be possible yet, but might be soon. At least there's people looking into it. And we can see how simulations of wormholes are already happening in quantum computers to show that somebody's working on entanglement there. So we have Ray Chow's gravity wave communications. These aren't entangled point to point themselves, but they're using entanglement basically to convert gravity waves to electromagnetic waves and vice versa. But this could be like lossless communication, because gravity waves may not interfere with matter. And so if you see Tim's talk with Raymond about this, there's a possibility for some kind of lossless communication across the planet without satellites. So you picture that over galactic distances. You have possibly some of the basis, still moving at light speed, but the basis of a high broadband communication system. And so we look at the counterportation from the previous examples with wormholes, and I recommend looking into that if any of you are curious and much more intelligent than me, I know, to look into that. And so we can imagine that there may be, are they just trading emails over long distances? Probably not. You know, they might be trading simulation packets or the code for their own algorithm to simulate their reality, to maybe not talk to each other directly, but talk to an AI facsimile of them in order to do hypotheticals, investigate hypothetical realities with all these others. I mean, we use the internet to game and trade virtual experiences with each other. It's not inconceivable, you know. If they're doing this, I don't think they're using IRQ. That's all I'm saying. They're probably something much more broadband than that, possibly with, you know, brain computer interfaces, neural integration, so it feels real. So the universe could be teeming with these kind of signals, carrying high resolution holographic experiences. You know, the holographic principle that there's possibly higher dimensional, more information coded onto a more liminal space, like you know, the computer interface that we use is as we know, a holographic projection of ones and zeros that are living on the surface of a disk, and those are, you know, by coding between those experiences, by packing and unpacking algorithms, we get the zoom and everything we know and love. But yeah, something like that, and we just haven't turned on yet. And is that, you know, a little aside here, is this sort of like what McKenna was getting at with what psychedelics more or less represent, that there's a network and there's these mechanisms that exist throughout nature, possibly for humans to engage with this network that's far deeper and much more advanced than we can possibly shake a stick at, although we might be getting to in our own crude limited, as the internet as we know it is a facsimile or a crude representative model of the larger internet that exists in space-time and in nature. We might have the ability to generate something like that, and those may go together. That might be full circle, like why life exists, to generate AI, to generate computers so that they can generate realistic simulations that end up recontributing to this universal mental network mind. And you know, I apologize for anybody that thought this was going to be a serious science talk. And so the other players in the game are just waiting for us to log on, more or less. Sort of like you have the board on one of your favorite online games if you play, and your friends are there, and some friends are not, and they're all, you know, the ones that are on there are like, oh hey, you know, you logged on finally. And there's our aliens. Possibly we've been NPCs until this point, and the visitors we talk about might be some of these holographic avatars experiencing our world remotely or through levels of simulation, as we talked about, nested simulations. So and that the next generation of internet, as we know, you know, maybe what if the next couple of generations of computers are, you know, these quantum assisted AI computers with real-time visualization and brain computer interfaces, where, you know, they're either hypothetically or actually connecting to aliens on the other side of the galaxy based on your preferences. And, like, you know, just like social media curates your friends that you might enjoy. I might enjoy this or that person. You might enjoy this or that civilization. Have you tried the Gorgolopsids from Alpha Centauri and XL6? They're right up your alley. It's far up, but conceivable. And just look at the jump in broadband signal as we get more computer processing and ability. We fill the gap we find applications for it, developers, and we get deeper experiences as a result. So I'm sorry I've gone so long, but I think I'm done. And that we have this leapfrogging and capacity, and that's followed by a depth of computing experience, and that's then followed by another leapfrogging of capacity, and that's it.
That's
See you out there,
amazing.
Space Cowboys.
Brendan, that is amazing.
Listening.
Well, thank you. Thank you for that massive presentation. I'm doing them a little bit different too. I'm putting the slideshows side by side. So it may look a little bit different in it, like when it goes up on YouTube, but hopefully it'll be a little bit easier. So I'm going to put this on gallery view. Everybody put your hands together for Mr. Brendan McNamara. Brendan, that was tremendous. Thank you, man. Thank you.
Thank you. Thanks for giving me the opportunity. I had
Yeah.
jitters the whole time.
No, you know what? A lot of that, it's like anything else. It's just practice, right? So in a sense, we're just kind of like Toastmasters here. You just keep doing it over and over again. Oh, sorry, still. Oh, you're muted again. Okay. Well, yeah. So I think we've probably got about 40 minutes, unless you guys want to close things up. Why don't I go to Drew in sunny Florida, who just put his hand up? And oh, okay. I'll change that so folks can unmute themselves. Okay. And actually, I have
I
two hands
muted
up
and I
as
got
well.
stuck on mute. That's why I couldn't answer.
You know what?
Thank
Let me
you.
go to Phil first. Phil has his hand up. Go for it, Phil.
Night, Tim. I'm out.
Oh, okay. Drew, have a nice
No.
evening, man.
Yeah.
Hey, man.
Drew, did you have something you wanted to share quick or?
I think
Okay,
I scared off Drew.
Okay. Shrish, do you want to go?
Yeah, does Phil want to go first or should I go first?
sorry.
Yeah, I can go first. I'll be quick.
Yeah,
And,
same thing. I have a few slides, so
Yeah.
that's about.
Well, and let me apologize if I scared Drew off. He was having connectivity issues, I think. He just kind of stopped and I thought he was done, but I guess not. So
there's a clash between me and Shrish, so you decide, Tim, who goes first.
Yeah.
Well, yeah. I mean, do you guys want to do short updates? I think we'll just keep things running until around 8, if that's cool. 8 my time, so it's in the about 40 minutes.
Yeah,
or
I
so.
think I've got about 5 slides and maybe a video to show.
Okay. Yeah.
Should I go ahead? Okay, let me just go ahead.
Yeah. Okay, Shrish, go for it, and then we'll hit Phil after that.
Okay, here it is. So what I wanted to share was, can you see my screen?
Yeah. Yep. And again, I've got these in side by side, and hopefully that it doesn't record the same way, but it should look okay. So
yeah, I think it should be fine. Yeah.
It should look a little more readable, and then people can see you better, which is why I'm doing it like that.
Yeah. That's good. Yeah. I think I like this. Yeah. So I just want to give an introduction to what I'm doing, since I've had a few discussions in our group a lot, and so I said, okay, maybe it's time. And we also started doing some work on the what I'm saying is putting it into practice. So it's still very early. So, but anyway, let me just start with an introduction. So this is what I'm doing. So basically, this is just a snapshot of what is Verlin's entropic gravity model. So 1 second, this is covering that. So Verlin entropic model. So basically, it's an entropic force, and basically, it says T is what is it? It's the under temperature. And you can see that what he mentioned is there's a gradient with the holographic screen. And delta S is proportional to mass. That is the particle that appears at the screen. Okay, and one of the things that he makes is T is actually the cause of acceleration and not an effect of it, which is quite unusual. So what I'm trying to show here is it's basically going to be two propulsion models. So this is what we have today. So just briefly, I'll just go. Body emits a particle, you get the particle momentum, then he says there's an entropy with the screen that I mentioned, which produces inertia, and the particle momentum's acceleration field results in the under temperature for this entropic force, and so we have conservation of momentum, and your rocket moves stuff forward. So this is what I call the serial model. Everything is based on that particle that is emitted, right? We know this. So I'm actually working on proposing a new model, which I'm calling as a parallelized model. So basically, all of the above appears in parallel, really speaking, okay, with the inertial background, inertial vacuum background. So as you can see, entropy, inertial momentum is basically the conservation of momentum input condition. I call it inertial momentum. You have acceleration field, and you have the under temperature all separated out. And it's kind of assembled by the inertial background, and you have to have the conservation of momentum as is normal for any inertial reaction, because inertia is Newtonian anyway. So that's what I'm proposing. So just some trade-offs which may be evident. The serial model, it basically scales with the mass flow. We know that because T is really small in comparison. So it's very rigid because everything depends on that mass of the particle that is being emitted. And well, it's easy. We know this since, I don't know, last century or maybe even before that. So then this parallel model that I'm trying to introduce is a low, very low entropy gradient, really speaking, but theoretically a very high under temperature is feasible. Okay, so that's what I mean by very high energy efficiency because of the nature of T, which is basically due to quantum vacuum fluctuations. Okay, and again, it's not system generated. What I'm trying to get at here for those who don't know is T is generated through the mass, really speaking, the mass that is emitted by your rocket, really speaking. So if you can do it right, that's what I mean. Theoretically, you should get almost an infinite scale. That's theoretically, really speaking. The big problem is how does one generate T without M? We don't even know that. So based on how we do that, we can drive massive energy efficiency, really speaking. And this parallelized model, as you can see, it's not rigid, of course. So that means you can manipulate it any way you want it, theoretically, really speaking. So highly flexible. It's complex, and as much as I know, it has not been done to date. Okay. So this is the next part of my work. So this one, this is basically the current model. Okay, this is kind of like what McCullough with quantized inertia talks about. This, you see this right black arrow. So that's basically the what he talks about, the under radiation. So then you have the Newtonian potential here, the A1 equal to grad phi, so which is normal. So what he's talking about is doing some kind of shielding, which will reduce the right side. So that means you should get larger thrusts, so basically higher efficiency. So I am going to move it into a little bit of a difference here. Okay, so what I'm talking about is actually introducing a negative inertia at the right side. So the left side is known. It's just the way rockets work today. We have the normal Newtonian potential, etc. On the right side, we have negative inertia. So everything is negative. So that means we should be having a negative inertia, which is A2. And so we have a positive gravitational potential, really speaking. So again, if you look at just on the surface, we should say this should be possible. There's no violations here, so to say, because as I mentioned, using the entropic model, delta S is proportional to M. So if we had negative mass, then naturally it should be a negative entropy. So that means it's a negative inertia. But the next part is going to say why we cannot use a mass, really speaking. So then I come to the Alcubierre drive based on gravitational potential that I mentioned. Supposing we're able to create what I'm showing here on the left side. I don't know if you can see my pointer here, but if you can create a very high acceleration field, which is much greater than the inertial acceleration mode of this one. So we have a non-equilibrium and equivalence principle, really speaking. And given the sign of the acceleration field that I mentioned on either side, the positive and negative, we have the curvature of Alcubierre, really speaking. So there's no positive or negative energy, no massive, it's just a regular propellantless inertial acceleration, but just with this non-equilibrium that has been introduced. Okay, so yeah, some of the problems which should be evident is, one, we got to introduce negative inertia without mass. We got to split the acceleration field, as I mentioned in the second diagram. And yeah, we need to have a propellantless conservation of momentum, really speaking. And then we need to have some way of sustaining this whole reaction, the York time that Dr. White has been talking about with the Alcubierre drive. And there must be some form of asymmetry here for directional control. Of course, benefits, it's really fully propellantless without violating anything, any laws. It sticks to the laws. It's non-equilibrium, but that does not violate any laws because we still have equilibrium recovery, really speaking. And it's a feasible Alcubierre drive without violating any energy conditions because, again, there's any question about the entropy conditions that I mentioned here. They are positive and negative entropy, which is not violating any laws of thermodynamics. As I mentioned, it's highly energy efficient and it's highly scalable. And of course, theoretically, I mean, not theoretically, it should be possible for not just space, but also terrestrial applications. Just brief overview of what I'm doing. So it's basically a thermodynamics basis, which should be evident. I have a parallelized propulsion architecture that I mentioned, and this non-equilibrium equivalence principle. So basically, this is based on a photonic model, and then there is some proprietary internal non-equilibrium that is being used to build this all out. And I would say the really important part is really this last one. There's a very unique method to produce this very scalable under temperature. So the most important thing when I was talking about it does not violate any laws, which is one of the big problems with propellantless. Usually it violates conservation of momentum. So it's a no-go, but this is not reactionless. So anyway, so just quick overview. I have some basic validation of what of this whatever I've been talking about. There's still some issues with, I use some internal actuators, so there's a whole bunch of issues. So that part is still being done somewhat manually at one side. There's a lot more work to be done in the photonic models. Then the Alcubierre drive is a bit fuzzy, still so to say at this point of time, because I'm using Arduino Mega as a controller for this, and I don't think it's able to handle the load that I'm putting on it, really speaking, for the Alcubierre mode, really speaking. Okay, so what else? So yeah, I will show it after this, and then I'm going to show both the inertial acceleration mode and the Alcubierre mode. But yeah, there's that portion which is kind of manual still. Hopefully that'll get resolved soon. And then I have an interesting test for showing the space-time curvature, and I will explain that when I show the video. That's it. So I'm going to show the video now. Stop share. Okay. Yeah.
And then this is the video for your quantum loop, right?
Yes.
Yeah.
So it's on my logo. So Tim, don't worry, there's no music or anything like that, right?
Oh, cool, cool. Yeah, I always worry about the copyright stuff.
Oh yeah, yeah.
Somebody
no, nothing.
mentioned
It's just-
earlier about, I think Brendan said, you know, will this ruin monetization? We don't monetize this at all, so I have no worries there. I just worry about copyright stuff in general.
Oh yeah, yeah, yeah. No, nothing. I remember this. You had mentioned this a couple of times before. So, and besides, I'm just showing a lab update, really speaking. So
Yeah,
no
no, that's
fancy.
awesome. Well, and so my hope is, again, what I'm doing this time around is I'm trying to put the videos, the slideshows side by side. And
Mhm.
that probably won't work for super math intensive ones, but I think for the stuff today, that way you will be bigger and, you know, and then the presentation will be a little smaller and it
Mhm.
should be a little easier for people to watch. So we'll see, and hopefully I won't get beat up for
I
it.
think so. Yeah, yeah. Anyway, here it is. Continue. Okay. Can you? Oh, sorry. I don't think I shared it. So, okay. Let me share screen. Oh, where'd that go?
Okay, and I'm not seeing it quite yet, but
Yeah, yeah. I was just trying to find the window. Yeah. Do you see that now?
there we go. There we go. Okay.
Okay. So it's a few minutes, I think 4 minutes or something. But disclaimer right in the beginning, there's some part of manual stuff. It's literally my first lab version, so to say.
Yeah, and
Okay.
now is there any audio? Did you share your audio or
I think there is
mic?
some audio in it as part of, because there's actuators going in it, but there's no, as I said, like no music or there's nothing from the
Oh
outside.
no, the only reason I ask is so with Zoom, I always miss this. There's a little checkbox when you share your screen that says share audio also. So you might want to, if it has audio that's worth hearing, you might want to
Oh, no,
stop
the
share.
audio
Okay.
is, I think, immaterial to most people.
Okay. Okay. Sorry for interrupting, sir.
Oh, no problem. Okay. I will talk through it. I mean, I'm talking there also. So this is what it is. So this is the first part, the actual normal inertial acceleration mode. This is what I mentioned. There's a lot of photonics there, LEDs. So it's going to just showing it a few times. I think this is the last one, I think. Yeah. Yeah. Okay, so this is the Alcubierre drive mode. So as it says. Yeah, Curtis, after this video, I will come to you. Kind of rough though. So this is the test that I mentioned.
Wow, this is interesting, Shrish. Well, thank you for playing this for us.
Yeah.
And let me see, Curtis raised his hand. So I think
Yeah,
after this,
right
we'll
after
probably
this
have to do a
video,
couple
I'll
of questions. Then we'll go to Phil, and we might be able to squeeze Drew in if Drew has, if he has a quick update.
Yeah, I'm not sure of how that curvature works in right now, but yeah. I think that's it.
Okay. Well, let me do this. Yeah, looks like we're just about there. Okay, we've stopped the share. So you know what? Let me put everybody, give Mr. Shrish Halla a big applause.
Thanks.
Thank you, sir. Thank you, Shrish. Let me go to I'm gonna jump right into questions. Curtis, I think, had a question for Shrish. And then Mike, I think, does too.
Yeah, so David was asking a question about audio. There's no audio, really speaking. So there's nothing.
What was
it's
that
put on
thing
it.
you were pressing down in the video?
So that's part of the non-equilibrium mechanism I have there, really speaking. So it's pushing down on a kind of a spring, really speaking. It's a soft material. Okay, so the issue with that is I need to have the right. There's a bunch of things I'm still evaluating that. Okay, so I'm thinking one is it could be the motion profile, it could be the reference frames because there's two inertial frames, right, at either end. So, but they are connected through the top frame, really speaking. So just kind of looking through all of those, or maybe the actuator because it's a regular servo, right? So
Is there
I
motion
don't
going
know.
on inside the device?
Yeah.
Okay.
So the other left side that you see, that is fully automated, so to say, but the right is not. The right is the positive entropy side, and the left is the negative entropy side in the video.
So you have mechanical motion happening somewhere in there.
Oh yeah. It's
Okay.
it's not solid state like I think like Drew's and a few others are doing something solid state. This is not solid state. There is mechanical, very much like what Mega has, right? You have
Yeah.
things happening inside. So there's a lot of things happening inside.
Okay. The other question I had, or the other comment I had was, you mentioned momentum conservation. And
Mhm.
I think anytime you think about those things, I'm not saying I have an answer, but when you think about those things and what we're trying to do,
Mhm.
I would go back to Noether's theorem. And so with the
Yep.
symmetries, one of the things about Noether's theorem is that if you have a system that is dissipative, that can break the symmetry. Meaning, I mean, the symmetry is not really broken, it's just that the energy goes elsewhere is the way I would think of it. So
Yes.
so
I've seen that dissipative model, really speaking, but I think this one does have because I don't think it is dissipative, really speaking, as much as I've studied it. It is, the inertial model is basically, it is Newtonian, really speaking. Okay, so we have to account for that in this, but not the gravitational frame because that's I guess it's non-inertial if I'm right, so.
Okay. Well, Shrish, thank you.
Yeah,
Thank you.
thanks.
So if it's okay, let me jump over to Phil really quick. And Phil, I think you had a presentation too for us, or you kind of had an update, right?
Yeah, most of an update, but I'm just gonna do a retrospect before, a quick
Okay.
retrospect of the experiment I done before.
Yeah, and we've got about 15 minutes left, and again, I'm not sure if Drew wants to squeeze in too.
Yeah, I'll be quick. I'll just because some people were not there last year, so that's why I wanted to do a retrospect.
Looks like it's dark. I guess it is dark. Yeah, because it's like 11 your time, isn't it?
Yeah, it's almost 11.
All right, out in Seattle, our sun is staying up later, so that's nice. Finally getting a little
Okay,
more
so
sunshine.
can you see that?
Yeah.
Yeah. So that was the grinder experiment I did last year, late last year. Some people might not have seen it, so that's why I'm replaying it. So we can see a weight loss here, and when the wheel stops rotating, it gains back its weight. So it's really a weight loss. Okay, so it's really a weight loss, and some people said, well, it might be the wind, and might be blah blah blah. So I redone the experiment. This is what the PhD of Lockheed Martin asked me to do. Clear, like a more clear evidence that the spinning wheel would alter the weight.
Now, Phil, if I could ask, especially since it's a power drill, what happens if you run it backwards? Same thing?
Yeah, that's the problem with the grinder is it's not made for this type of experiment. And if I did flip it the other side, and I still got a weight gain. Actually, it gains weight this time, and I still got a weight gain if I flip it on the other side. But it's more there's a distance between there's a greater distance between the disc and the balance if I flip it the other side.
Okay, so it does do the same polarity of effect, though. That's kind
Yeah,
of
so I was thinking that it would lose weight if I flip it the other way, but it actually gains weight as well. But by the way, my theory is that the energy density acts as like gravity also. Electromagnetic or gravito-electromagnetic energy densities is gravity. That's what it is. It creates time dilation, temperature change, acceleration. So that's what it is. And right now, this is a little how do you call that? I forgot. The interferometer and magnet experiment, where I move a magnet close to a laser. So and we see the laser moving as well. So the interferometer is very sensible, extremely sensible. And when you have an energy density of any sort, then you're gonna see the laser moving. So right now I'm moving up and down a magnet close to the laser. And we can see the laser kind of moving a little bit. So I'm not touching anything, and the mirrors, they have a non-magnetic frame, or nothing is affected by the magnet. And so now I have this experiment. I already showed this before, but it's very important because that's the Cavendish experiment, and it's affected by light, which is a electromagnetic energy density.
Deflection, an attraction towards the bulbs. I also tried putting the arrays of bulbs inside of the box with the balance Finally, I tried putting,
So anyway, you tried a lot of stuff, but that's basically the idea. When the light goes off, the pole is still attracted because it still emits infrared light. So yeah, and now the moment. The final experiment where there's no wind. This is the MHD vortex experiment of liquid gallium. So you cannot have any wind interference. And there's no eddy currents interference as well, because I redid the experiment when the gallium is at solid state. And nothing is moving when it's at solid state. So I'm right now for 5 seconds and I'm inputting 120 amps DC for 5 seconds, and you can see the weight is shifting. And I did it on I flipped the current, and I did get a weight gain as well. So I still got a weight gain. So you can see it gains weight again. So I need to, I was expecting a weight loss, but I need to consider the interference of the magnet and things like that, or have a higher current. But we can see a weight shift of the apparatus. It's pretty obvious. There's no wind, no eddy currents interference. So, I mean, it's clearly caused by the gravitomagnetic energy density that is created by the gallium spinning in a vortex. So that was the lab update, and I did update the manuscript as well. And here we can see the energy density limit. I calculated the energy density limit. I also figured out that the gravitational constant of Newton is not a constant, but it's a variable proportional to the mass of the sun, proportional to the maximum energy density and the mass of the sun. So that suggests that we'll have to investigate all this, but I want to say that the gravitomagnetic permeability is very low indeed, but there's also a relative gravitomagnetic permeability with a high standard deviation, extremely high standard deviation. And also I wanted to suggest that the magnetic permeability has been tested. Is based on a test, but it's based on a test on the surface of Earth, but we could definitely test it on the International Space Station as well, to see if the gravitational potential changes the magnetic permeability. I'm very curious to know that. So that's an experiment proposal to the International Space Station right there. And I calculated that the maximum energy density is something around 2 × 10⁵ joules per meter square, which is very close to the energy density of a neutron star before it collapses into a black hole. So it's a solid constant. It's a constant, it's a calculated constant right here. I also wanted to show that the gravitational time dilation, right here is proportional to the gravitational potential energy. And the gravitational potential energy when we talk about time rate and speed, it's all about you use the you need to use the kinetic energy equation and solve the V right here, and we can see that when we convert when the gravitational redshift is caused by the photon is losing electromagnetic energy because it gains speed. So that's why that explains the gravitational redshift right there. So there's no loss of energy. It gains speed. It loses electromagnetic energy because it gains speed proportional to the first order. So that explains the gravitational redshift. So yeah, there's 5 minutes left, so I'll let Drew do his presentation.
Awesome. Phil, thank you. You know, since we're clapping today, everybody, quick applause for Mr. Phil Bouchard. Thank you. And Phil, thank you again. Drew, let me apologize for squeezing things. Do you want to do a quick update for us before we close things out?
Sure.
Okay. Sorry about earlier. Your internet cut out, so I thought that you had changed your mind or stopped or something. So go for it, sir.
I'm looking to see how to share the screen. Let's try this one. Can you all see the screen?
Yeah.
Okay. Since we're up in the bar on notes or field notes, I decided to pull the header off of our presentation. But shortly, this was I don't know, yesterday, day before. This was a test. Started at 0 newtons and ran up the voltage, and then basically I checked the system to see if it's charging up the field capacitors or not, and it was. So I ran it up and down over the course of about 6,000 seconds, just taking a look at the system in general, seeing what it was doing, how fast it was doing it. When I got all done, I basically had 2.21 millinewtons of thrust with power on, 1.7 millinewtons of thrust with power off. Power off thrust just means that there's charge trapped in the materials, and they're in such a way that they continue to produce thrust because all of the geometries of thrust generation is being met. So they'll continue to produce thrust until the charge bleeds out of the materials, which in a high vacuum takes friggin' near forever. I've had plates stay charged for 2 or 3 months. Anyhow, 22 newtons is basically 225 milligrams of thrust. This plate weighs 360 milligrams at 62.6% earth unity. Question is, what can you do with 62% earth unity? Well, we've been going along since this chart started in 2014, but we've been doing this 5 years before that. And as you can see, we're progressing towards Earth Unity line. So that's a spacecraft that could launch from my parking lot and go up into orbit and fly around the solar system. Right now we're at 62%. That's my rated. That's what I'm declaring is where we're at. And this is just a shot of the test apparatus with this particular plate sitting there in the back. So what does this buy you? Well,
yeah, Drew, let me apologize. Your audio is cutting out a little bit. You might try turning off your video.
Turn off my video.
Oh, now it's perfect. I don't know what you just changed, but
it's phone conduction headsets. Is it still good?
Yeah. No. Now it's great again.
Great. Okay. So what does 62% Earth Unity propulsion buy you? Well, it's in a system today, you could make a 45 metric ton spacecraft with a 20-ton dedicated crew payload. That's enough dedicated payload mass to support a 4-person crew for 30 days. This craft would be capable of sustaining 0.4 gram or 0.4 G's Earth reference acceleration. As the propulsion system uses less power than a laptop, it never needs to be turned off. This means a Mars level gravity the whole trip, soft landing on anything that's Mars sized or smaller, and most importantly, it means flush toilets for the entire trip. And if you don't think that's important, go wear a diaper for a couple of weeks. So the question is, where can you go in those 30 days of air on your spacecraft? Well, let's see. You can go to Mars and back 5 or 7 times because it's 3.27 days to Mars. That's low Earth orbit to landing on Mars. 3.27 days at 0.4 G acceleration. 0.4 G acceleration is a little less than the propulsion system can make, but you got to account for the rest of the mass of the spacecraft. Where can you go in 30 days? I personally want to step on Titan and come home and brag about it. So I can get to Titan in 13.2 days. Of course, it's 13.2 days to come back home. So that should be just inside my 30-day window of air. That's it. Any questions?
Yeah.
That's
I
absolutely
had a
wonderful.
quick question for you. I know we're running out of time, Tim. Can I just ask this quick
Yeah, go for it. Go for it.
question? So 45 metric tons, and you showed some test results of 1.7 something millinewtons, right? So I'm just trying to understand how that works.
You scale up.
No, you say like the tests you showed was something what, like 1.7 millinewtons, I think? Or no, was it, or was it 200 millinewtons? I don't remember. Sorry.
We're talking about a piece of plastic that you can put in your pocket at the moment.
On your slide, you showed some test results, right? It's whatever it is, it's in the millinewton range, right? I mean, so how do you go from this millinewton to 45 metric tons? You know, that's a lot of thrust.
Scale up.
Can't hear you.
Oh, he's saying you could scale it up.
Ah, okay.
When I say the word scale up, I'm working with a small unit. There's nothing stopping me from building one the size of my house.
Ah,
Except
okay.
the cost.
Okay. So 45,000 kgs, that's going to be large. Yeah, I see what you mean.
Yeah.
It's roughly 22 feet in diameter, about 40 feet high.
Okay. Okay.
Awesome. Well, guys,
Okay,
again,
that's great.
Yeah, we're just over 8 o'clock. So I think, why don't we close things down for today? I don't want to forget to do this though. Since we're clapping today, we got to give Drew a hand as well. And you guys should give yourselves a hand. This conference event, this is yours. This is all about you guys and what you do. So, man, you guys blow me away. I mean, day after day after day, it is exciting to see all this stuff move forward. I truly mean that. It's a humbling experience. So thank you for letting me moderate. Okay. Well, guys, it has been a wonderful, wonderful evening. And so our next session is April 13th. Things are crazy busy. So I'm completely booked on presentations for April. And then I have folks, I'm like halfway booked for May. And tonight, I didn't even expect it. We had like 5 different people present, so it's exciting. It is so exciting to see all this move forward. So for the time being, everyone, thank you very much. This has been APEC Open Mic for March 30th, 2024.